Let's start so that we don't accumulate again delays. I promise I'll do a better job. So, allow me to start, and I would like to continue now with a session on innovations in hydrogen infrastructure. Maybe we can close the doors because it's. Let's close the doors. Yeah, let's close the doors. Okay, so we learn in the morning about the program in general, and we look at the production. Let's move into the, if you want, supply chain along the chain, and let's look into the hydrogen infrastructure, logistics, distribution, storage. We learned also from the colleagues in the Joint Research Center this morning that this is the most diversified portfolio that we have. And I know it's going to be an impossible job for you, Dionysus. But I would like to introduce another member of the team, Dionysus Tsimis. He's the lead of the infrastructure portfolio in the joint undertaking. And he will guide us through the analysis of the portfolio in the program, but also have some outstanding projects presenting and a bit of a debate. And really my pleasure, Dionysus, to give you the floor. Thank you.
Okay, hello everyone. So thank you very much, Mirella, for the introduction. As you mentioned, we'll be dealing in this session with hydrogen infrastructure. So we'll follow the same example as we did in the previous panel. We will hear 4 different project presentations. And then we will go into a panel discussion with all the projects. But before that, I'll give you a brief overview of what we're doing in the program along these 4 key themes that we will hear about today. So basically, what do we mean by hydrogen infrastructure in our program? When we talk about hydrogen infrastructure, we'll basically talk about distribution and storage. So we're talking about large-scale storage, above-ground storage, underground storage. We're talking about liquid hydrogen carriers, hydrogen transport, be that by pipelines or tube trailers or whatnot. Key enabling technologies such as compression, purification, and metering solutions, and hydrogen refueling stations that we need to improve for the heavy-duty applications. So in this section of our program, we have 42 projects funded for 165 million euros. Unfortunately, of course, I will not be able to cover all the projects in my presentation, but I'll try to give you a key overview of these 4 themes that will be presented today, along with some achievements along the way. So I would like to start with the first theme, which is dealing with hydrogen storage. And here, basically, on the left, you see a depiction of everything that we're covering in our program. We're trying to focus a lot on underground storage solutions with the repurposing of depleted gas fields, salt caverns, and soon we will have a project that will be designing a low-cost solution for mine-lined rock caverns. Besides the underground part, we're also dealing with above-ground hydrogen storage, and in our program, we're mostly dealing with innovative solution offered by metal hydrides. And I'd like to go into a bit more detail into the underground part. And I would like to share with you some results from our first demonstrator project, Project Hipster, which finished this summer. It is our first big demonstrator, relatively big. It stored 3 tons of hydrogen, which is very small compared to what we will see in the future. But it still showed some impressive results with respect to the cyclic operation and the pressured cycles that the cavern underwent. It performed 100 cycles from 110 to 150 bar in a period of 6 months, and it showed no problems in dealing with these pressure fluctuations, both underground and in the above-ground infrastructure. It also performed a techno-economic assessment, analyzing 7 different archetypes of caverns, and it came up with a range that you see on the screen from 16 to 29 euros of capital cost per kilogram when we're dealing with salt cavern solutions. Why do we have a range? Because different sites come with different costs, and it is heavily influenced by the cavern's volume, but also by the cavern's depth, and depth is actually a more important factor. So we did have some very good results. They also showed that repurposing a natural gas salt cavern can offer a 25% reduction in the capex costs. But not everything is perfect, of course. There's still room for research, and we do have challenges ahead. Here I point out two main challenges. One in the micro scale, looking at bacteria microbes in the storage media that we know can pose an issue and a threat to the hydrogen that is stored there. And we will have a dedicated solution, a dedicated project which will characterize these processes and come up with risk mitigation strategies, Project Hydra. In addition to this, I present a macro challenge that we are faced with, and that is to scale up. So if we look at the natural gas storage industry for salt caverns, it took them about 50 years to come up with 244 terawatt hours. And according to the net zero scenarios, well, they're conservative and different estimates, but a rough estimate is that we will need around 300 terawatt hours of hydrogen storage. So we will need to scale up significantly and significantly faster than what the natural gas industry did. And so far, we have only 9 terawatt hours announced by 2030. So we need to accelerate as much as we can. We're trying to do our part in the program by supporting two flagship projects, Fridge and EU Stars. Fridge is a direct result of Project Hipster, building on the results of Project Hipster, and we'll be testing a salt cavern in Manosque in France, two neighboring caverns actually, where the hydrogen will be cycled from one to the other. And together with, it will also replicate these results in two sites in France and in Germany, with a cumulative capacity of 20,000 tons. And also, apart from the work on salt caverns, we do have work on depleted gas fields. We'll have Project EU Stars presenting today, which will give you more details about that. But it's a very, one of our important projects. It has already a demonstrator in Austria. And together it is preparing 4 replicators that can accumulate to 26,000 tons. So some work done from our side to accelerate these deployments. Moving on to the second theme of the presentation, which is around high pressure logistics. And here, of course, we need to have reliable, cost-effective, and high-performant compressors. We have been funding a lot of projects on this topic. A series of our cosmic series of projects has now scaled up to Cosmic Demo, 3 projects in succession funded by us. And now the solution is finally installed in a hydrogen refueling station in France. We will hear more about this project presented today. It will be in the panel, so I leave more details to be presented later on, but it's important to state that already a patent has been awarded for this work. Next up, we also need to adapt our hydrogen refueling stations in the gaseous supply chain to be able to deal with the heavy-duty requirements. So we need to have high refueling rate capabilities. For that, we had 2 projects, Pride and Ready. Pride developed the protocols, and now Ready is testing these protocols by manufacturing the necessary components and demonstrating these high refueling rates. You can see here already the tank storage test system that can accommodate 100 kilograms already manufactured, and we'll begin testing. Finally, we're also looking at the overall logistics, looking at how we can most effectively and efficiently deliver hydrogen from production to the refueling station. That is done by hire. And Project Road Trip, which is looking at developing improved tube trailers. And they have already manufactured their Type 5 tanks that will allow them to go to 700 bars. And with this, they can enable a 1,500 kilogram payload capacity. Moving on to liquid state. Here we're looking at what we're covering in our liquid hydrogen infrastructure. We have quite a comprehensive approach. Starting from liquefaction, we have an innovative project called Hylical, which is looking at a magnetocaloric liquefier. It's a huge jump in the state of the art. The state of the art right now is around 1 to 2 kilograms, and we are looking to scale up to 100 kilograms per day. And we're targeting the ambitious KPIs that we're already mentioned by Darina from the JRC this morning. They're quite ambitious. A good point here to point out is that as soon after the project started, ENGIE New Ventures decided to invest in the startup Magnotherm, which is a good sign for the startup ecosystem around Europe. And moving on to the storage part of the program, we have there two projects, Nikolai and LH2 Craft. Nikolai is focusing on the insulation concept itself, which can be applied to either stationary or mobile applications. And LH2 Craft is looking at an entirely different design, which will be tested at 180 cubic meters and will be have potential scalability up to what is equivalent to an LNG tank. Finally, on the refueling aspects for liquid hydrogen, we also need to scale up there. We need to provide liquid hydrogen to our heavy-duty applications. And here we have Project Deliver, which is looking at designing a hydrogen refueling station that will be able to refuel up to 5 tons per hour and is targeting a zero boil-off through their innovative boil-off gas management system. These are all fairly new projects. We have the opportunity today to be able to hear some more results from Nikolai, who will be presenting today. And finally, the fourth theme is around hydrogen carriers. We know that they will probably play an important role in the imports of hydrogen into Europe. On the top left, you can see a graph there from the Global Hydrogen Review from the IEA. I know you cannot read the legend, but the blue is ammonia, and it's looking at trade flows from different regions across the world. You can see ammonia playing a dominant role in the future, and for that we have two different pathways investigated in our program. One is the proton-conducting electrochemical reactors, projects Winner and Single, who will present today, and the other is the catalytic membrane reactor through Project Andrea. But besides ammonia, we're also investigating other pathways such as liquid organic hydrogen carriers. And here we had our first system demonstrated with a project starting in 2017. It was demonstrating a full storage and release system, but then we decided to go back to the drawing board and looking at how to reduce the critical raw materials of the catalysts. And already now, Project Unlocked has achieved a 10-fold reduction in the use of platinum with equivalent performance. And these three projects that you see at the bottom, Single, Andrea, and Unlocked, are all aiming at the same targets of demonstrating a 10 kilogram per day prototype, looking at these ambitious KPIs for the hydrogen delivery costs and the overall energy consumption. So this brings me to the end of my presentation. I'd like to give you a very short but spherical view of the four themes that we'll be hearing about today. So I would like to thank you very much for your attention. And yeah. And I can immediately give the floor to the first speaker, who is Benedikt Hasibar, who will be presenting our first theme of projects on storage, underground storage, EU Stars. Benedikt, the floor is yours.
Yeah, thank you. Thank you, Dionysis. I just grabbed the hand mic. I hope I'm not too nervous to jump around here. Thanks for having me. It's my first time in Brussels, and I'm happy to give some insights into our project EU H2 Stars. The title is European Underground Hydrogen Storage Reference System. So what we are doing is we already have an underground hydrogen storage in place. It's a demonstrator plant, and we want to make a blueprint out of that to deploy it to all around Europe. To my person, I'm Benedikt Hasibar. I've been working at RAG for 4 years now, and I'm project coordinator for our green gas projects. RAG Austria is a gas storage operator. It's the largest energy storage operator in Austria, and we're happy to change our systems from natural gas to hydrogen. About EU H2 Stars, well, the project started in 24 and will go on till 29. And here on this picture, you already see a first site of our underground hydrogen storage demonstrator in Rubensdorf in Upper Austria. If any of you managed to come to Upper Austria, I'm happy to give you a site visit there as well. All right. Who are we at the project? It's not only us as RAG Austria. We are 11 partners from 5 European countries. It's 4, besides us, it's 4 other storage operators in the Netherlands, in Spain, and in Hungary, and 1 technology provider from Poland. We also have some infrastructure, meaning pipeline infrastructure, ATGM as the Austrian gas grid operator, Linz AG as an energy utility, and also some scientific part being coupled by Energieinstitut and Montan-Universität. What are we doing in our project? The core is our demonstrator. You just saw the photo of it. It's a demonstrator plant for the underground hydrogen storage. It's a repurposed underground reservoir where natural gas was found some decades ago. So the natural gas was withdrawn, and now this reservoir is able to store hydrogen on a seasonal basis. So the idea is to store hydrogen there when there is a so-called excess energy in the system, and withdraw the hydrogen again when there's the need for more energy, when the demand is higher. We have this demonstrator running, and we also want to build this blueprint, as I said. So we're doing upscaling and optimization of this demonstration. The upscaling has already been done for 2 Austrian sites. One is a repurposed, already existing underground natural gas storage, and one is a completely new site developed for hydrogen. And there are 3 replicators, 1 in Spain, 1 in Netherlands, and 1 in Hungary, all with different settings, where we also want to give the basic design for those sites. But it's not all. We're also thinking of how underground hydrogen storage fits into the future energy system. So is there the need for hydrogen storage? And I can tell you, yes, there is the need. So the systemic need is there. And here we want to show how does this need really look like, and how do storage profiles look like when they are set into this setting. We're also thinking about reliability and security. So safety measurement, safety is always a big topic in gas infrastructure. And within the project, we are developing standards and norms to give for a secure storage operation. Last but not least, on work package 1, we're thinking about stakeholder integration. The key buzzword here is social embeddedness. So not only acceptance on the social level, but also embeddedness. How does this fit into the overall system? Those 5 content-filled work packages are then surrounded by our dissemination, exploitation, and communication, and headed by the project coordination. The next slide gives the same thing I just told you, just for those who couldn't follow because I was too fast, to read it afterwards. But one more thing to tell about the demonstration. We plan to do 4 seasonal cycles within those 4 years, so each year 1 cycle, and show what happens in the underground. 4 cycles at our demonstrator site, 2 cycles at the Hungarian site, which is being developed. That's what we are planning to do and already doing. Coming to the project results so far. For the operation of the demonstrator, the first cycle is running. So the injection was completed with September, and the withdrawal will start just next week on Tuesday. And we are very excited to see what happens there. I just want to mention one thing here, because in the morning session we heard a lot of the electrolyzers having some troubles, not with the stack itself, but with the balance of plant. And we heard on the reasons for that. We also have some problems. So that's something nice that unifies us. The not so nice thing about it is, that it doesn't have anything to do with the project. We just want to demonstrate that we can store hydrogen. We didn't want to be an expert on the production side. Well, we are now. And in this case, also it was not the stack the problem. The problem is that within 2 years, for the second time now, the, how's it called? Where the electricity comes in the that transformer. Thanks for that was helping me. So the transformer unit just was damaged, a total damage for the second time, and this just is not helping with such projects. Nevertheless, we managed to store 500,000 cubic meters of hydrogen, so 500,000 cubic meters of hydrogen within our storage. We are capable to store 1 million cubic meters in this site. And just to give you some numbers, here we can store 1 million cubic meters. Thinking of the replicator sites, we're talking about 100 million cubic meters and beyond. So there's some scaling steps to be tackled here. For the replicator sites, we already finished the basic engineering for 2 sites, for Austrian sites, and the other ones in the other countries I mentioned are running. And also for the safety issues, the first MMV plan for our demonstrator is already been published. You can find it, and the link I will present there. Yes, to the other points, the embeddedness, the social embeddedness was assessed for Austria, and also for the storage profiles for the underground hydrogen storage are developed. And here, most important, a nice picture again from our site. This was 2 weeks ago, and just a nice rainbow over our site. Yeah, I just wanted to share it with you. Okay, we publish a lot of our results, and they can be found here. So everyone interested into underground hydrogen storage, the importance of it and how it fits into the system, just follow the link. And for my last slide, I will come to the project impact. And as there's only 45 seconds left, I will keep it short. Our project has scientific, industrial, economic, and societal impact. But the most important thing for me to say is that we know that there's this systemic need for underground hydrogen storage. This is important. And we know that we are technically feasible to do it. So it's we have the know-how and we have the materials to store hydrogen. And we also have the sites and the geology in Europe to do so. The one thing that's missing is the business case for it. So if there's no economic value behind it, well, it's getting hard. But we're working on that, and maybe we'll go into detail on that in the discussion round. Thank you.
Thank you, Benedict. I'll gladly follow up that in the panel discussion. So for our next speaker, I would like to invite David Colomar to present the Cosmic series of projects.
Thank you, Dennis. So where is the mic? Should I use just this one? Or?
I think you can leave them two like this.
Yeah. All right. So, hello everyone. My name is David Colomar. I'm the coordinator of 2 of the 3 projects that are presented here. And I'm representing here today the coordinator of the third project from IFER. This is Mr. Rami Shaori, who unfortunately could not make it today. So it's me jumping in and telling you, having the pleasure to tell you a few words about Cosmic projects, and in particular the Cosmic Demo project. So this is a project about innovative compression technologies, and not only making it, but demonstrating it into a real site. So I will not speak too much about technical details of the project, because this has been done quite a few times already in the previous project, but I rather focus on the achievement of this series of projects. So first of all, we have to understand why we do what we do. So we all know that there is the big topic on hydrogen production. I think this is something that is really in the focus on the CHGU activities for a very long time now. On the other hand, we are also very well aware that end users are a key component of the hydrogen value chain. But sometimes we forget slightly that in order to connect the production of hydrogen with the end users, we need something in between, and this something is logistics. And when I say logistics, I'm not only speaking about hydrogen trailers or pipeline, but I'm speaking about something that we need to bring this hydrogen from the production to the end users. This is compression. And in any case, whatever means we want to have to transport the hydrogen from A to B, we need compressors. Some people could say, well, wait a minute, if you liquefy the hydrogen, maybe you don't need compressors anymore. But if you look with a little bit more details in what is a liquefier, you will realize that a liquefier is nothing but a big group of compressors that work together. So basically, even in the case of liquefaction, you need hydrogen compressors. So everywhere in the logistic of hydrogen, we need compressors. And interestingly, this compressor is one of the key problems, or one of the key remaining bottlenecks of the hydrogen value chain. So why is it like that? Well, actually, it's quite interesting to see that compressors are pretty much the last mechanical part of the hydrogen value chain. If you look at production, you have, and the end users, you have mostly electrochemical system, electric system, thermal system, etc. We have barely any mechanics left, except here in the compressors, where we have pistons that push the gas, or either directly or on a membrane, or these different ways. And these compressors have moving parts. And within the moving parts, there are interstices, obviously. And because hydrogen is a very small molecule, it likes to leak inside these interstices, producing wear and tear issues, maintenance issues, leakage issues, safety issues, reliability issues, availability issues, etc., etc. Plus, we have a high electricity consumption. And not surprisingly, this is where one of the biggest source of trouble happens in the value chain. So with the Cosmic series, what we have tried to do is basically to solve the problem of compression by replacing a mechanical system by a non-mechanical system. And how do we do that? We use so-called metal hydrides. So I won't go into too many details, but just very shortly, can imagine you have some metal alloys that have the ability to absorb hydrogen in the structure. This is, by the way, already well known for storage purpose. And when you heat up these metal alloys, you can release the hydrogen at high pressure. So you absorb at low pressure, you heat up, you release at high pressure, you have a compressor. But now this compressor has no more moving parts, and that changes everything, because since we have no moving parts, we have no leakage, no safety, no noise, no vibration, no civil engineering cost, no wear and tear, no loss of availability, etc., etc. So basically, we solve pretty much all issues of the hydrogen compression by replacing mechanical compression by non-mechanical compressors. There is only one problem left. Unfortunately, today we are not yet able to perform compression with non-mechanical solutions above 500 bar. That means for the last part of the compression requirements, we still need mechanical compressors. So here we are with the Cosmic concept. What we do is basically we use non-mechanical hydrogen compression to compress hydrogen from the source, large-scale non-mechanical compressors, to compress hydrogen from the source pressure to an intermediary storage at 450 to 500 bar. And at this pressure, we can already meet the requirements of 350 bar refilling, plus the requirements of filling centers and injection into pipelines, etc. And for the last part, for the 700 bar refilling, we add a small mechanical booster that does the last part of the compression. You may think, well, wait, we still have to do 50% of the compression because we are only at 500 bar or 450, and we need to go up to 900 or 950. But actually in compression, what matters is not the difference in pressure, but the ratio. So the ratio that remains to be done from 500 bar is only a factor 2 to reach the 900 bar. That means it's basically very small compared to if we had to compress from the source. So basically what we do here is we have a concept where we use a large-scale non-mechanical compressor to do most of the job and a small booster to do the last part of compression, where mechanical compressors are actually not so bad. So this is the concept of Cosmic Demo. So as I said, we have a series of projects. In the first Cosmic project, we have developed the technology, we have demonstrated that it works at small scale, then we had to scale up to meet the requirement of industrial needs. And then in Cosmic Demo, we further scaled up, and most importantly, we demonstrated under real-life conditions. That was the target of the Cosmic Demo project. And this is what we've done. So we have a consortium of 6 partners from 3 different EU countries, Denmark, Germany, and France. And we have a site in the center of France where we have installed and operated a hydrogen filling station with also on-site filling center to distribute hydrogen to some remote users. And we have been testing various kinds of mobilities, ranging from small hydrogen bikes up to large garbage trucks, using also taxis, utilities, small and large utility vehicles, etc. And by doing that, we have demonstrated that not only the technology is in theory working, but also operational and applicable to real-life applications. And we had also a filling center on site to supply, as I said before, industrial clients. So here are a few pics of what has been done. Of course, we had to do some further R&D at the beginning of the project to further tune, let's say, the recipes of the metal hydride. We had to do the engineering calculation to prepare for the system. We had to build the system that were built in the east of France for the metal hydride compressor and in Denmark for the mechanical boosters. They were then installed on site. There was a lot of certification, authorization, permitting, etc. And then finally, we could inaugurate the station that was done earlier this year. And the station is currently still running. So here is a picture of the installation. What you see on the left part, I don't know, do I have a laser? Yeah. This is the metal hydride compressor. We have here the mechanical booster. We have here 2 nozzles at 350 and 700 bar. And we have various integration components, storage, cooling, etc., etc. Here again, I'd like to make a focus on this compressor. This is, just to be clear, in terms of pressure and capacity, by far the largest system that was installed worldwide in hydrogen, in non-mechanical hydrogen compression. So this is, I believe, quite a success story, and this is something that I think the Clean Hydrogen Partnership can be quite proud of, because as you see, it's a long-lasting story, but at the end of the day, we have something that is ready for commercialization and that is ready to hit the market. So very few KPIs or very few highlights of what has been achieved in the project. So of course we've, one very important stuff was, of this project was to demonstrate that not only the technology works, but that also it is in line with all existing regulations. So we not only certified the compressor itself, but also the entire refueling station containing a metal hydride compressor. That was not a piece of cake. We needed some time to discuss with the authorities that, of course, had never seen such a compressor before. And by the way, one feedback is we need to get involved in the ISO working groups to also adapt the way how the standards are written to take into account that they are not only piston compressors, but also technologies that work without moving parts. This is quite important. We have discovered, this was not anticipating so well, that the civil engineering costs are strongly reduced by having non-mechanical compressors, because we need no more reinforcement of the beton, so of the ground preparation when we install non-mechanical compressors compared to mechanical compressors. That is a huge contribution to cost savings. Installation and commissioning lasted for less than 1 month. This is also a big improvement compared to state-of-the-art technologies. We performed CEP tests to demonstrate that not only it works, but also it provides the same quality of service as reference technologies. and we showed very high availability. Just a few interesting KPIs or performance indicators that we observed. Here, for example, you see a pressure curves over several days. And what we see is that there are some fluctuations, some slight fluctuations in the pressure. This is due to the fact that we observe an impact of the ambient temperature of the performance, because it is a thermal system. When, for example, it is a little bit colder during the night, we observe a slightly better performance than when it's hot. This was observed in the field. Also, what we see here is the filling curve of the compressor, is the compression curve, of the compressors to fill up a storage downstream. What is interesting is with non-mechanical compressors, we have actually no fixed compression ratio. So that means the compressor adapts to the end user needs. So when you have a low end user pressure, then we produce a low compression ratio. When the pressure of the storage increases, then the compression ratio in the compressor increases as well. That makes the station and the compression process very efficient. Yeah, and that's it really. So few next steps. Of course, we need to further scale up the technology because there are some needs for even larger systems, as what we have done in the series of projects. We need also to adapt to other cases beyond mobility. And then we need to replicate and commercialize. And as you see, the technology is ready. So, for example, in the frame of H2 Valley project, we are confident that this technology could be a very strong added value for some of the projects. So I'm pretty sure there are some people involved in H2 Valley projects here today. If you want to discuss the implementation of the technology in your project, please feel free to speak to us. We'd be more than happy to do so. Thank you very much.
Okay, thank you very much, David Colomar, for the excellent presentation. So we'll move on with the next speaker, which is from Project Nikolai, Robert Eberwein. Please, you're welcome on stage to present this novel installation concept that you're developing.
Thank you very much. Yeah, let's come to my topic, energy transportation and storage with liquid hydrogen. Let's start a little bit dry with theory. Hydrogen we can store in general in three forms. Once we can store it in the gaseous form at ambient conditions, but here we have to increase the pressure to achieve high energy densities. Then when we cool it down up to minus 253 degrees Celsius, it will be liquefied. That's this we name then liquid hydrogen. And there's an area in between, which is the cryocompressed hydrogen. Here we have very cold conditions, but also very high pressure conditions. But we see also a lot of technical problems have no space, as we see it here in the car. So the tank is often limited, and so we need a fuel that has a very high density and it allows to store a lot of energy on a small volumina. And here, liquid hydrogen comes into mind because that's a possible solution. As we started the project in 2024, the project, the world was a little bit different. Here, we think about to import the hydrogen to Europe by pipelines. Then the Ukraine crisis started and we see our pipelines are not very safe. It could be damaged, and we have several risks that are connected to this. Then we see, okay, but what is now a more flexible way to import energy? And this could be the bulk transport by ship. This is possible, as I have presented in the previous slide, by liquefied hydrogen, which has very high energy densities and allows such an import of energy. But the ship is one problem. I have also to build the infrastructure therefore. So I need storage tanks at the exporting country and storage tanks at the importing country. So the problem has two sides. Once we have to deal here with mobile tanks and also stationary tanks. And this is where the project Nikolai comes into mind. Furthermore, we see that cryogenic fuels like liquid hydrogen are well accepted today. This is thanks to the implementation of LNG that was done in the last 2-3 years. So also here, and we see from other PhD theses that the safety is also very good. Furthermore, we see from other projects that liquid hydrogen is a well opportunity because the import itself could be cheaper than compared to other delivery rates like ammonia or methanol. And we see also from these projects that perhaps we can adapt the existing LNG infrastructure to liquefied hydrogen. But how the storage of liquid hydrogen is arranged today and why we need new solutions. Typical liquid hydrogen is stored today in double-walled tanks. The double wall is necessary to have here a vacuum which is combined with an additional filling material to create this very high thermal insulation. This setup is applied since decades. It works, but we have the usable volume is very low compared to rectangular shapes, which we have, for instance, in ships. And we see that the production time of these tanks is very high. So it needs here sometimes up to several years. And the quality assurance is also a problem because we have only one space with vacuum. If this, if the outer wall or the inner wall is damaged, the vacuum is lost, and so also the insulation. And this means you have here a problem. In the project Nikolai, we want to change the state of the art by a very cheap solution. We are interested to build tanks by a one-walled system, so that we have only an inner wall. Primary, the idea was to have an inner wall, which will be insulated by several vacuum insulation panels. A vacuum insulation panel is nothing else than a package of powder coffee. Yeah. Here you have, in this package of powder coffee, you have your porous fill material, and this is, and around this you have a gas-tight envelope, or a gas-tight membrane. And by this concept, it is possible to bring the fill material under vacuum, and this is at the end the same concept as we see it today by the double wall, but only you can apply it in a system that you can produce in an industrial environment. You can automate it, you have a very good quality assurance, and so on. So an ideal product to increase the production of liquid hydrogen tanks in the future. So, but all in all, vacuum insulation panels, or VIP, is only a concept that is not defined by a package of coffee. Yeah? It depends on the envelope that we can use, which could be from different materials. Here today, polyester, like in a coffee package, or stainless steel is an application. We have to think about the core material, which will dramatically affect the insulation performance. And we have to think about the shape and its dimensions, and how we want to mount the vacuum insulation panels. So the vacuum insulation panels is not a new technology. It is used today also in the transport sector, for instance, or in the housing sector. But for this, what we want to do here to store liquid hydrogen is completely new, because it deals with completely new temperatures, new materials, and new questions to the material. Within the project, or the project itself, comes from TRL1 and will achieve at the end TRL3. So it's a very fundamental project at the end, but we deal in the project with a very holistic view on the problem. So we have in mind that the solution will be applicable at the end to ships and also stationary tanks. That's our aim, but that's the application in the future. In the project itself, the state-of-art investigation is very important, because it's not the first investigation in this direction. And so we can learn here from promising or non-promising concepts that were investigated in the past, and we see also which methods are possible to implement, to develop such a new insulation. Based on these methods and our key performance indicators that we get here from the Strategic Research and Innovation Agenda from Hydrogen Europe Research, and our own key performance indicators we developed in the project, we deal with the development of new concepts. And these concepts will be benchmarked in the project by the different work packages within the project. Very important here is the insulation design, the circularity and sustainability analysis, as well as the safety and the proof of concepts that will be arranged within the project. The outcomes will prepare the implementation of such a new insulation system. Here we are interested to create, until the end of the project, a design guideline as well as recommendations for codes and standards. One promising concept is presented here on this slide. This based on a double-walled system with a membrane in between, and this builds an insulation for a liquid hydrogen tank based on an inner and outer insulation, and in both insulations or areas of the insulation, vacuum insulation panels will be the primary insulation. This concept comes then without vacuum in the insulation areas, only in the vacuum insulation panels. So the system itself does not, there's no need that the system is gas tight. We can produce vacuum insulation panels in parallel, bring it to the installation place of the tank, install it, and we have very fast produced an own tank. This concept and other variants of this concept will be evaluated now in the project and benchmarked to each other, what you can see here in the picture. So here you can see some inspirations, what we have arranged until now. So I will not go into details and diagrams. More, we take a look in the project at the insulation material itself. So here we do thermal investigations as well as fatigue investigations. We deal with the circularity and sustainability on material level. We have arranged a safety investigation, and that's further ongoing with large storage tanks. And at our test site in Berlin, we are building up in time a large test rig that allows us to test this insulation concepts on a surface by 2 by 2 meter. Very important for the project are our key performance indicators. Here we are targeting a CAPEX price for the tanks of €20 per kilogram hydrogen in 2030, as well as a boil-off weight in storage percent per day of below 0.1%. Today, it looks so that we can achieve these key performance indicators, especially the boil-off, and we are dealing further together with the industry in evaluating the CAPEX costs. The industry is in the project very important. It is part of our stakeholder advisory board, where we have also members from politics, academics, technical regulators, and other projects. We meet around every half year or in bilateral meetings and have a very good effort to discuss here the relevant points and bring the project forward. Thank you for your attention.
Thank you very much, Robert, for the excellent presentation. And now we can move on to the final theme, which is around ammonia cracking. And I would like to invite Selene Hernandez to present Project Single.
Thank you. I hope you can hear me. Yes. Okay. So thank you. My name is Selene Hernandez Morelludo, and I'm a research manager at Costec Membrane Sciences. And today I'm going to present the project Single. Single is the electrified single-stage ammonia cracking to compress hydrogen. Single, it is coordinated by us, Costec Membrane Sciences, together with partners from different countries in Europe, from Spain as CSIC, and GCRIO and Universidad Politécnica of Catalunya. We also have University of Ljubljana from Slovenia, SINTEF in Norway, and ICONS in Italy. The project started in May 2023, and it's going to last for 3 years, so it's going to end at the end of April 2026. So before going into the details of the project, I want to explain why we want to use ammonia as a hydrogen carrier. So ammonia is a carbon-free liquid that has high energy and high hydrogen density. It has a well-established infrastructure, so because we have been using ammonia and transport ammonia for over 75 years for now, and we can use that infrastructure. And also its property make it easy to storage and transport. In single, we use that we call the proton ceramic electrochemical reactor, PCR. And with that, we can produce a high purity compressed hydrogen in one single step. We can have the ammonia cracking, the ammonia dehydrogenation reaction. We can separate the hydrogen. We can manage the heat in a micro level, and we can compress the hydrogen. All that with superior energy efficiency. So the main objective of the project is to prove that we can use these PCRs for ammonia cracking and obtain high purity pressurized hydrogen. To demonstrate that, we are going to produce a module that is able to produce 10 kilos of hydrogen per day. This module is going to be located in Valencia, in Spain. Additionally, we are evaluating the value stream for scale-up economic and future large-scale deployments. But how the PCR works for ammonia cracking. So this is a schematic of how a PCR cell looks. It's a like 4 centimeter tube, and it is made by 3 layers. We have the porous support, that is a nickel barium zirconate composite. Then we have a dense layer made with barium zirconate, and then we have an outer electrode that is made with the same nickel composite barium zirconate. So when we feed ammonia inside the tube, the ammonia cracks on the nickel sides and form hydrogen and nitrogen. And then when we apply current into the membrane, we are able to extract the hydrogen formed inside the tube, and able to extract it to move it to the other side of the membrane in the form of protons, and then form hydrogen and compress it. So the outlet of the reactor is mainly pure nitrogen. Doing this, we can shift the equilibrium of the reaction, so as we see in the graph on the right. So by removing the hydrogen, the ammonia conversion increase, so we can reach almost 100% conversion with above 95% hydrogen recovery. Additionally, applying this current also gives Joule heat to the membrane, and that heat it is provided to the endothermic reaction of the ammonia cracking that gives a higher hydrogen energy efficiency. So here there are some examples of how the PCR performed under ammonia cracking conditions. We saw that we can have wide operation conditions, so we can operate on a wide range of temperature. Here is this example of 600 and 700 degrees. We can also have a wide range of pressure, so 15, 20 bars. We have a flow and fall flexibility, so we can operate at different residence times. Also, the ammonia can be dry or it can be wet. And if we scale up this technology to one plant that is 1 ton per day, our models predict that the energy efficiency is going to be really high. So we are close to 95% efficiency. So to functionalize these cells, so the results I present until now, they are in the cells. So to functionalize these cells, we make that we call stacks. So the stack is made by barrels. One barrel is 6 cells together with a seal, with a glass seal, together to interconnect, and then the barrels are sealed all together. All this is made in our manufacturing line in Kostek Membrane Science in Oslo, in Norway. So why we want to have this stack is because we can have the 6 cells. It can be electrically in parallel, but the barrels are connected in series. And that is why we use this nickel here. It's a nickel-based interconnect that allow us to have efficient current distribution between all the cells and also give mechanical robustness to the stacks. These stacks are designed for high pressure operation, and they are designed so we can have a U-bend flow. So the ammonia goes from the inlet up to the bottom and then back. So we can have a micro heat integration. So the cells that that provide heat are close to the cells that they need heat. So this is a high efficiency stack. So one stack, 6 barrels stack is able to produce half kilo of hydrogen per day. If we put 5 stacks together, it is like we call a panel. And if we put 4 panels together, we have the module that we are going to make in single. So that will produce 10 kilos of hydrogen per day. The status of this module is that the ballast plant, it is ready, and it has arrived to Valencia. It arrived like 2 weeks ago. And the module is being produced as we speak. So the plan is to be delivered in Valencia at the beginning of the next year. And then when we have the module all together, so we will plan to run in, and these are the list of the targets that we want to achieve. So we want to have energy efficiency more than 90%, high ammonia conversion more than 99.5%, hydrogen recovery more than 95%, more than 500 hours continuous operation, and get hydrogen purity according to the ISO standard for fuel cell. That means 99.97% purity. Other project outcomes that we have developed during this time is so we also have proof. We tested a stack under ammonia conditions, so we proved that we can use the stacks for ammonia cracking. So we got a 99% ammonia conversion and more than 98% hydrogen recovery, with a stable operation of 100 hours. We are producing the stacks, as I said before. And also we did some research on the optimization of the catalyst, on the nickel barium zirconate support by metal infiltration that allow us to decrease the temperature of the ammonia cracking. With this we can go to lower than 600 degrees. We have studied the resistance of the different alloys to try to identify a metal that will resistance to ammonia. So we identified alloy 625, and this is the one that we have been using for the ballast plants and for the module. In parallel, we have done some advanced model and process control that will allow us to enable maximum hydrogen output, even if the fluctuation with the renewable power. We have done sustainability validation and techno-economic analysis that show that we cover the threshold of the RED 3, and also that the modular PCR architecture supports distributed hydrogen generation close to where the demand is. If you want to know more about the single and these outcomes, we just published a set of info pack that you can find in our single Zenodo community. So here is the QR if you want to go there and just read a bit more in detail what I just explained. And just as a closing remark, we are preparing a new project as a follow-up of this single that is going to produce 100 kilos of hydrogen per day, a demo unit located in Germany. So with this project, we are going to move from TRL 5, so this at the end of single, to TRL 7. In principle, it's going to start next year, and it will last for 3 years. Thank you. And thank you to all the partners in singles as well.
Thank you, Selene, for this great progress demonstrated. And actually, don't go too far, because I would kindly invite all the speakers to join me on stage for this quick panel session. We have until 3:15, I'm told, to take a couple of questions. So please join me. You can have a seat in these comfortable orange chairs. Benedict, start with you, since you're closest.
All right.
So I showed that we have a net zero scenario where we will need around 300 terawatt hours of storage demand. How likely do you see that happening from your side? And what do we need to do to accelerate it?
Well, there's this goal, and also for 2030, there's another number I didn't have in mind.
By 2030, 9 terawatt hours have been announced.
Yeah. Well, on the technical side, that's possible. So we have the geology for that in Europe to provide those storage sites. It's just we need the commitment, the financial commitment, and the uptaker commitment from companies, from energy utilities, and from governmental side to develop those sites. The thing is that infrastructure development takes some time, and if we start developing it the moment we need it, we're too late. So we have to go in advance and develop the infrastructure now, so we can have it to be a puzzle piece of the future energy system, the renewable energy system. Yeah.
So it looks like almost storage site operators need to take a leap of faith and move forward.
Well, we are.
Yes.
We are, but we are limited. So there needs to be the commitment from all sides.
Is there anything we can do to support this business model development? Do you have any advice for us on this matter?
Well, I think the most important is to raise the awareness that infrastructure and from my view, especially the storage infrastructure, will be needed, and to get commitment from all sides, from producers, from uptakers, and as I said, from the governmental side as well.
Okay. Clear. Thank you.
Thanks.
I'd like to jump over to you, David. We saw your project being mostly focused so far around mobility applications, and I was wondering if you are considering any other possible applications, like, for example, storage, underground storage of hydrogen. I read recently in the report that about 50% of their capex costs are accounting for compression costs. So it seems like there's a big piece of the market there for you.
Thank you. I wanted to go to you later to discuss, so of course. So yeah, obviously, other applications beyond mobility are completely possible. They are even easier to do than mobility, because most of the time the pressure levels required are lower. So in the case of underground storage, it may be even possible to use only the waste heat of the electrolyzer to supply the compressor. So that could be a very interesting use case. So I'd be very happy to discuss this. So yes, of course, pipeline injection, underground storage, but also some industrial applications can be very interesting. Just as an example, we had recently a very nice chat with a developer of a offshore wind park, and they said they want to bring the hydrogen from the offshore wind park down to the shore by pipeline. And on their platform, they have big issues with vibrations, and therefore non-mechanical compression is a very interesting topic for them. So there are plenty of possible use cases. And yes, of course, the target is to have generic solutions that meet all the requirements.
Thanks, David. So, Benedict, you're interested?
I'm very interested, yeah.
Great. So, Robert, over to you. As we see with liquid hydrogen, I showed a picture from the IEA. It looks like ammonia is dominating right now the future projects for imports of hydrogen. What do you think from your side are the major bottlenecks for liquid hydrogen infrastructure that we need to solve to reverse this scenario?
Yes, thanks for this question. Bottlenecks, it's very difficult here because it's not the typical chicken-egg problem that we have to integrate a new technology. It's more than this, because we don't have a technology that we can implement into the market. And what we see in time is that we have worldwide several projects that are dealing with exactly this topic, but all of these projects are TL 1 to 3 projects. So at the end of these projects, there will be not a product that we can bring to the market. Mm-hmm. Yeah. What we see is, what could be useful here is an approach that we have 4 solutions, and we have to find out which one is the best. So if it is the solution by vacuum insulation panels, then it's the question if we are well prepared for this. So in Europe, we have several manufacturers for vacuum insulation panels. Yeah, so here we have to go a little bit more into detail, how we can manufacture it, how these companies can support us, if vacuum insulation panels are the solution. But on the other side, again, we are here on a very low TRL level, and with TRL3, it's not a technology which is so far developed that the industry is interested to push this forward. The industry, what we hear in the project is they are listening. They are listening what we are doing, how this could work, and so on. But we are too early to bring it to the market. I think here we need more nationalities. And also, when we speak about an energy import to Europe by liquefied hydrogen, we are not talking only about Europe. We need the liquid hydrogen somewhere. We need a producer that is producing the liquid hydrogen and is willing to ship it to Europe. So I think that's a world problem that we have to solve as a world problem together.
Okay, thank you, Robert. And Selene, from your side, looking at the ammonia cracking business case, we saw how dominant the ammonia imports will be. From your side, how quickly do you think you will be able to scale up to be able to capitalize on these developments? Do you think, yeah, you can give us a timeline from your side?
So from our side, so as I say, so with Single, we are going to reach a Tier 5, and we are preparing now a new project that is the plan is to have a demo for 100 kilos of hydrogen, but to test this demo in a more industrial relevant conditions. So connect it to the ammonia pipeline and use the hydrogen directly on site. So that will give us Tier 9 at the end of the project, that is 2029. And after that, we calculate that maybe 1 more year to have early commercialization. So maybe we say like full commercialization after 2030, more or less.
Seems clear. Thank you. And I would also like to open to the audience if there are any questions from your side to the speakers. Yes, please.
Yeah, it's Michael again, and it's a question to David. First of all, thank you for your presentation. It's good to see that the metal hydride compressor topic is taken up again. In 2013, Heiss Dorsis, IFE, High Gear, and you know them, we developed the first metal hydride compressor. But an issue we did not solve is, how did you solve the accumulation of impurities in a metal hydride compressor? As a metal hydride compressor is a marvelous purification system for hydrogen.
Yeah, you're right. It's a tricky question. Frankly speaking, we haven't solved it yet completely. Yeah. So at the moment, that is also one reason why we started by focusing on mobility applications, because there the purification requirements are anyway quite high. So we are not inducing additional purification needs. In fact, we still struggle with some impurities. So when we have very high level of water, for example, or of oxygen, and of course not to mention hydrocarbons, this is still an issue, because then we see that with time the performance of the hydride degrade. That's clear. On the other hand, there are also ways to regenerate the hydrides, and these we see. And in fact, the chance we have in the compression is that the compression process is actually a very nice combination of parameters to regenerate, because we have temperature and we have pressure. So we can play a lot with these parameters to regenerate. So these we have already experienced quite a lot. So we have made significant progresses. But yes, to be fair, we are not yet able to absorb any hydrogen stream, and especially when it's mixed with other gases or a large concentration of impurities.
Thank you. Any other questions from the audience? Again?
Now,
a follow-up question.
Elena, the question is,
Selene.
you said that you are producing hydrogen at a grade that you can put it into a grid.
Yes.
how do you safeguard the topics of a grid? So how do you safeguard the technical rules that are relevant for distribution grids? You were talking about the distribution grids, not about the hydrogen backbone, for instance.
Can you repeat? I think I lost you.
One of your last slides, you showed that you can also inject, or you might inject hydrogen into the grid. So not directly connecting to a fuel cell. So how do you safeguard the quality of the hydrogen you are injecting into the grid? Because you have to meet technical rules that are binding for the distribution grids.
Yes.
It's the same story that you from RAC Benedict have to cover as well when you release hydrogen from the storage into the grid.
Yes, but in our case, the technology we have, so we can get really high hydrogen purity. So the only impurities you will have is just, if you have, it's just nitrogen.
Yeah.
Maybe I will continue with the purity question on the underground hydrogen storage. As we are using depleted gas reservoirs, natural gas reservoirs, there is some residual gas inside, which we get out with every storage cycle. And we were afraid that the share will be quite high, but with the first 2 cycles we saw in the previous project, in the first 2 cycles, we saw that we are on the lowest at 98% of hydrogen, so meeting at least this grade. We'll see which grade will make it to the overall grid, but yeah, that's what we are all going to. But in the end, we can also add on a purification system. This adds some costs as well. That's what always to mention.
It's from the release, but not in the injection, so you have to meet several requirements. But thanks for the question.
I just want to add, so for we had also used our PCR technology with other fuel like natural gas, and that in that we use 99.99% hydrogen purity. So we are quite confident on our technology and the purity that we get.
Great. Thank you for the questions. And I think this brings us to the end of the session. I would like to thank you, all the speakers, once again for the excellent presentations and the good exchanges. And
Thank you.
thank you.
Okay. There's not much time until the coffee break, and I hope everybody will have a coffee so that we get a bit more engaged, I would say. So let me, before we do that, before we go for a coffee to wake up, let me try to bring one more expert talk in this afternoon. And I would like to invite on stage Abel Enriquez. He's the director of ENOH, how I like to say it, but I'm going to say what that is. European Network of Network Operators for Hydrogen. That's a pretty new established network. And Emilio Nieto. He's the general manager at National Hydrogen Fuel Cell Technology Experimentation Center, CNH2, in Spain. So I let you to chat a bit for 10-15 minutes and tell us about innovation for building the backbone, the so-called backbone. So, please.
So sit there or?
Yeah, sit there.
Yeah.
I take the phone first, so I will start. So it's a pleasure to be here. And I think we have also only 10 minutes before the coffee break. So I know I see your faces, so it's I need to coffee quite cold. 15, okay, that's fine. I think it's very good to have the opportunity to be with Abel and this new infrastructure or new body within the Commission in order to have him the opportunity to explain us which are the main trends and the main emission from this new body. And later on, I have at least 2 questions, and you also have 2 questions for me also. So please, start with try to explain all of us which are the NO. I don't know how to pronounce it.
Yeah, I know it's not easy. So very good afternoon, everyone, and thank you very much for the invitation. Thank you, Valerie, for the opportunity to present NO, NOH, call it as you wish. in the office we say ENO. We are a new body, a new statutory body, which is being created according to the EU regulation. So my name is Abel Enriquez. I'm the Director General of this new entity. And I have prepared for you a few slides to animate a little bit the presentation and the introduction to you. So I don't know whether, yeah.
You can sit there.
So today my main target is to let you know that we exist, what we want to do, and why we need to talk more. That's why the research and innovation community and the infrastructure community needs to talk more. If I click next.
Yeah, it works.
Yeah. So ENO is the European network of operators for hydrogen. The name was decided by the Commission, not by me, so you can talk to them if you don't like it, but this entity has been established according to the gas and hydrogen decarbonization package. In 2024, the regulation was adopted. And we are now getting more operational with already the team being established and ramping up our capabilities. Our main mission is to promote and facilitate the development of trans-European hydrogen transmission networks, the big networks, connecting our member states and moving hydrogen from those places where hydrogen is produced at a lower cost and moving this hydrogen to the places where hydrogen is needed, like the demand centers. So our mission is to facilitate the deployment of this infrastructure, and for that we have received concrete tasks from the regulation. What you can see there, it's a family of entities. Maybe you are familiar, if you are in the energy sector, with ENTSO-E, the electricity transmission networks, with ENTSOC, the gas transmission networks, or with the DSO entity. So we are the fourth member of the family. A family of 4 entities working together to facilitate what is called the energy system integration. Our future energy system needs to be optimized to deliver our energy and climate targets at the lowest societal cost. And for that, we need a combination. We need a combination of pipelines, gas, hydrogen, and also electricity at both levels, transmission and distribution. So as you can read on the slides, energy system integration is part of our DNA. And we want to promote this idea when cooperating very closely with our sibling organizations at European level. Who is behind ENO? At this moment, ENO covers a group of 37 entities from 26 member states. These entities are today gas transmission operators, but all of them, they have ambitious plans to develop hydrogen in the future, to develop hydrogen supply corridors, and to develop a hydrogen infrastructure will be needed to facilitate the emergence of this European hydrogen market. In some countries, our member is not the gas transmission operator, but already the hydrogen transmission operators, because in some countries they have already decided to establish legal entities for hydrogen. So it's a large community of infrastructure companies, very much committed to deploy hydrogen and to advance the development of the future trans-European energy network system. A few words about our tasks. We have a number of tasks. They are in the regulation and they are described there. And these tasks are, let's say, grouped in 4 blocks. The first block, that one on your left, is about what we call the hardware. We need to planify, we need to modelize the future transmission network at the European level. And it brings with a lot, it comes with a lot of different deliverables and tasks that we will need to develop in cooperation with all our members, but also with a lot of stakeholders. Second block is about network codes. It's what I call the software, the rules that will define how the future trans-European network system will work. A molecule moving from Portugal to Poland will have to follow these rules, harmonized at the European level. Because everything which ENO produces, it goes to ACER, the European Agency for Energy, Electricity and Gas, and then to the European Commission, and becomes binding legislation through a delegated act. So the preparation of these network codes is originated in ENO and then goes to the Commission, which transforms this into binding legislation for the whole Europe. And then the third block is, I'm on my back. It's about, let's say, system operation and transparency. And there is where we can maybe talk more with you. And we have to do it. The regulation imposes on ENO concrete tasks on research and innovation. And these are related to hydrogen quality, hydrogen purity, as well as cybersecurity. But yes, we see a number of areas where certainly the cooperation can be enhanced and where innovation is needed. Leak detection, improving our compression capabilities, let's say, working also in the future materials. There are a number of areas where certainly more innovation can be really valuable. Although I have to say that the transmission activity as it is today has already a very high TRL level. In the northern part of Europe, we have already 1,500 kilometers of hydrogen pipelines in operation. So it's something that we know really well. And with that, I don't want to consume more time. Yes, I finished my introduction, but again, with an open hand to cooperate with the research and innovation community, letting you know that we are there. We are already 8 people in the team. The team will continue growing, and we are working very closely with all the stakeholders, with the Commission, and in order to facilitate and to accomplish our mission. Thank you.
Oh, thank you. Thank you for the introduction. I mean, the first question I have taken notice has been already replied, so we need to save some time. But what is also important for us is, the hydrogen purity is very important for us. And also, you know that the European Clean Hydrogen Partnership are working with many projects and different kind of overview about the different aspects covering the whole value chain. So how is possible? I mean, I trust on you. You have 4 institutions. I hope you will cooperate on a real basis. But what is possible for the European Clean Partnership try to help you in order to improve this hydrogen purity when you are trying to go to the network? Like it is?
So it's a very good question, and I have only a few seconds to answer. But indeed, hydrogen purity, it's one of the key elements when it comes to safety, interoperability between networks, also between installations, storages, transmission networks, terminals. And that's why there are concrete provisions in the regulation tasking ENO to prepare some initial studies. And the first deliverable comes in May 2026. By next year, we have to deliver what is called a hydrogen quality monitoring report. And this report will be published by May. There will be a public consultation before of 2 months, and we are planning to prepare also some workshops to cooperate and to work with the whole industry. This report is not the end of the way. It's just as the first step. For sure, there will be later some standardization. The regulation also foresees that the Commission can ask Sense and Elect to prepare some standardization. But certainly, the idea is to have some common, let's say, common level playing field at the beginning of our industry, which will facilitate later on the development and the cross-border flows across Europe. That we have the opportunity to do it well from the beginning, and we will try to take it.
It will be fine. Many thanks. I don't know if we have time. He has two questions. We are not sharing a little bit new things, but...
So, Emilio, for me, as National Center for Hydrogen, you are a national entity, and sometimes when you are working at the European level, you are not so close to the national entities as you would like to be. What I would like to hear and to ask you also to give us our views about what kind of barriers, technical, commercial, regulatory barriers do you see today when we try to put together and to join, let's say, local production, storages, and transmission networks? And then what is the vision of you as the National Center of Hydrogen in the cooperation with other ones at the European level to advance and how you can fit our work at ENO level?
Okay, good. Good question and very broad, so I will try to make a small brief only in 1 minute. I mean, we have 3-4 projects already before, and you can see that not only the European level, they are the people working in order to improve the technical barriers, but one of the main issues is the cost. So we need to put the hydrogen into the place, into the need of the industry in order to move ahead. And this is something that we all want to collaborate. Of course, we are coming from Spain, and in Spain, we are not cooperate like in some parts of Europe. I think we need to cooperate more, and this kind of new infrastructure, this is something that is absolutely impossible to build alone. So we need to cooperate between countries. We need to try to use this lesson learned from the different experience we are performing in the different countries in order to move ahead. And from the technical point of view, not only talking about the cost, is also how it's possible for us in order to put more volume into the networks, to try to do on a safety way, and try to increase the speed and also the pressure within the different tubes. I'm not talking about only materials, but also how it's possible to put more inside the tubes and try to make different kind of tubes. And the second point is hydrogen purity. I mean, all of you know that not all applications need the same quality of the hydrogen, and this is something we need to think about in order to put the hydrogen into the factory. If the factory needs, like mobility, for instance, 4 nines of purity, or needs a quality like, for instance, the blue hydrogen or the low carbon hydrogen, and how it's possible to put this within the tubes. And I think this kind of 3 or 4 points for me are the most important points. I think it's okay?
Yeah. No.
No, for me it's okay. I mean, I don't know if any one of you have some question. I saw your hand raised.
Wait for the mic. Now.
Hello, thanks for a good presentation. John from DTI in Denmark. So I'm happy you elaborate a little bit further on what is more important in terms of hydrogen infrastructure, because I think, I'm not sure whether purity is actually the major concern here, because a lot of the hydrogen is going for industry in Europe, which I think can use less purity hydrogen. But how are you going to help to advance the build-out of infrastructure, which is really what is needed to be able to deliver cost-efficient hydrogen to industries in Europe? So how are you going to enable that process? I think that's where we really need some speed. I come from Denmark, where we are eager to export green hydrogen to Germany, but all the TSOs are looking at each other, and nobody's really doing anything. I think that they're saying they want to spend a lot of money, but nothing is really happening. So how are you going to fast track that process? Can you do that?
I mean, what we can do is to prepare the plan to show that the infrastructure which is being planned makes sense, that this infrastructure is needed, that there are potential supply and potential demand to be connected, and therefore we can also run simulations and all the modeling to demonstrate that, yeah, it makes sense from the economical perspective. In your case, Denmark is one of the front runners today. They have concrete projects backed by the government, and at this moment, EnergyNet is publishing information packages for the development of the grid. On the other side, of Germany, the German government has also put 20 billion on the table to develop 9,000 kilometers pipeline in Germany, what is called the core network, which hopefully will connect with Denmark. Our role is to demonstrate that these connections and these networks make sense, that they are interoperable, that hydrogen can flow from one country to another based on common rules, common standards, and that's what we will do from our side. But yeah, it's for these networks to develop is more than Eno just pushing them. We need also the governments, the support from the Commission, and probably a future European mechanism for financing and de-risking these networks. So we are there, but as I said, we're not a superhero. We need also, it's a joint effort between all parties. Thank you.
I promised I'd do a better job, so let's try to stop in time. So really, thank you very much, Abel. Thank you very much, Emilio. It's a bit, you may say, and maybe we should have benefited more from a discussion such full of information. But you can also understand it was so difficult to make 2 days packed of information. I mean, we just mentioned to you, we supported at least 400 projects and many other things. So very difficult to spend a lot of time on each point. But thank you very much. And I already have 2 ways in which we will collaborate. So one, you may consider joining our stakeholder group. Second, let's talk about the next work program in 2026, where we will have to talk about the purity, building on the report that the European Commission did with you together. So really, yeah, a lot in front of us. Thank you very much again. Now, let's have coffee. And like I said, we still have a lot, including the awards. So let's try to have a coffee and be back at 4 o'clock. Thank you. I go on the low side. You want to do something with you for sure? No, but this way, maybe. We'll send you an invitation. She's gonna send you that email.
No, I was already in the presentation saying, after this presentation, they told me that I have to send an invitation.
Yes. So she from my team will send an invitation. And then expecting you. Yeah. Yes. Send and thank you for your time. Yeah.
I was here. I know. And you become one of the so we just got so on. You're asking to do something.
It's okay.
Another question from microspheres is also, what is the microspheres because these are hollow microspheres, but as a gas molecule, how does this regulate as long as you objective is to be reversed, this fast possible
So in that case, I mean, this tank should be information. So yeah.
I will completely not say that this is so I like the strategy that we follow these
That's the question of
No, no.
The guy from Russia, you know.
Ah, okay.
I don't know his face, but I'm sure he's in the room. The only one to see was a foreign. But the port of Valencia was missing a few years ago.
And I haven't seen, yeah.
Yeah, it's.
Speaking of Okay, so let's take our seats silently. Okay, I see coffee works. So, okay, so, like I said, thank you very much for being back in the room. And like I also said, try to take our seats silently, because I would like to start with the last part of the day. It's the last session of today that will focus on hydrogen for mobility. And I have the pleasure to introduce another team member, Lionel Boyot. He's a project officer on the transport side. And Lionel will have the pleasure, hopefully, to give you an overview of the project portfolio on the mobility side, and also to guide you through some presentations and a panel discussion. Lionel, the floor is yours.
Thank you very much, Mirella. Ladies and gentlemen, sit back, relax, enjoy the session. We'll be talking about hydrogen for mobility. 1 hour and 10, you know the music. There will be 4 project presentations. The coordinators will highlight their ambition as well as their achievement. Later will follow a Q&A session. And in order to increase the engagement, as Mirella said, please already take note from now on of your questions. So I will privilege questions from the audience above mine. What I wanted to say as well, yes, this session, next slide please, somewhat.
It's here.
Thank you. Mobility, hydrogen for mobility, it's a collective effort. In fact, we are 4 project officers in this pillar, if you want. So I thank a lot of my fellow colleagues, Pietro Caloprisco, Luca Feola, they're there, and Anna Sin, Anna, who is somewhere. So thanks a lot. I'll give you a flavor, an overview, the essence of it. Mobility is one of the 2 end use of the research and innovation agenda of the joint undertaking. You see in there building blocks and 4 transport applications. Each of these 5 items has some key performance indicators attached to it, target to achieve by 2024 or 2030. The cohort of projects, the core of transport is roughly 30 projects. But in the presentation, I've put 46. So we need to define a bit of a methodology classification, how to tie these things. I propose one classification, which is the following. First, the components, so the catalyst, MEAs, fuel cell stack, balance of plants, that need to be improved up until to the system level, where they would be tested either on bench or into world or European class prototypes. Then we move toward the deployment and the rollout from 1 unit, if you want, ships, up until hundreds in the case of the buses. And it's not just a linear progression. There is as well a feedback loop from the application, goes back into the component system. That means a seed today will flourish tomorrow, and there will be several harvests across the seasons. The next slide I'm going to present is about the fuel cell research, or the so-called building blocks. You do remember in the past we're talking about the triangle, the lifetime, the cost, and the performances. Let's put two more angles to it. We reach a pentagon by including manufacturing and as well as the integration validation. So on the component, we've been looking at how to reduce the use of critical raw material, platinum group metal above all, looking at to the fundamental of the reaction within this fuel cell, mostly PEM. And that was the focus of two projects, Camelot, further FC. Then we go into performances, how to make sure we have fuel cell stacks that are high power for the application that requires them. So a lot of power in more power within the same surface, if you want, or same power in smaller surface. This was the subject of Project Dolphin and Real High FC. Then 5 projects looking at durability. Keep in mind, in the predecessor joint undertaking, focus was on automotive, so number of hours were 5,000, 8,000 hours, something like this. In this clean hydrogen GU, we look into heavy-duty trucks, 20, 30,000 hours. There is still job to be done for continuity of the GU, looking into aviation and maritime, 40, 80,000 hours of lifetime and durability. Manufacturing, it's another element to reduce the cost, economies of scale, produce the same type of equipment or product, or you reduce the manufacturing time, increase the quality, reduce scrap, these things. Up until the validation, where, for example, fuel cell stack would be defined to fit into whatever type of application, like small size, medium size, large size. That was the focus of STASH, for example. This was for the building blocks. I now move into the non-road. In order to decarbonize isolated site, like a field in agriculture, a port, or a construction site, we have been supporting projects looking into fuel cell development for these applications. Fuel cells that will sustain harsh conditions, the dust, the moisture, the salt, the vibration, the shock in there. You will hear later on from project H2 Port. A bit down, there is nothing more annoying than to be waking up at 5 o'clock in the morning by a garbage truck, very noisy. Therefore, Revive as a solution for you. 11 of these garbage trucks have been deployed and put in operation in 5 European cities, and not only to reduce the noise, but above all, to reduce the emissions. We now have data from the operation of these garbage trucks, more than 12,000 hours of functioning, and an amazing 49% of efficiency, including the auxiliary, meaning the press, the compactor for the garbage in the back of the truck. 2 flagship projects that you are aware of, Jive 2 buses. This represents about 2/3 of the entire fleet of hydrogen buses in operation in Europe, roughly 250 buses in deployment, many millions of kilometers accumulated, thousands of hours of fuel cells in operation, and many of the sites, because these 2 projects are now finished, have compromised to continue the operation of the buses. For some sites, to expand their hydrogen bus fleets. And the last months of this project, we're looking into the demand creation, commercialization of the hydrogen buses in the east and in the north of Europe. We now move toward trucks. H2O, 16 trucks, 140,000 kilometers accumulated so far. There is a full dedicated presentation later on by the coordinator. 2 types of OEM, Iveco and VDL, retail and industrial site type of operation. But what is interesting is the next step. So 16 is nice, but a relatively small number. H2 Accelerate is aimed at putting 150 long-haul trucks around 10 T corridors in Europe, 8 member states, 5 10 T corridors. Synergies with Cinea for the refueling infrastructure of these trucks. Let's move into the seas. We have a 360-degree view from hydrogen system to hydrogen ecosystem, meaning what? We do support projects looking into alternative powertrain, PEM fuel cell for maritime application. You will hear from H2 Marine. Next year, there will be 2 new projects, multi-megawatt system powertrain for maritime. How to store hydrogen on board these vessels, either to power it or to transfer hydrogen as a bulk from one continent to the other. We do have projects looking at this. Nikolai was one example earlier today. Project on how to refuel or bunker liquid hydrogen on board these vessels. Demonstrator going from 1 to 5 fluvial, coastal, or short sea vessels running on ammonia or on hydrogen, be it liquid or gaseous. And as well, non-technical regulatory work done by HiShip, a project which was instrumental to provide feedback to international maritime organizations. Good news 2025, interim guidelines for the use of fuel cell on board vessel has been adopted, and the interim guideline for the use of hydrogen as a fuel on board vessel has been adopted. HiShip contributed to this. Now we go into the port. Once the vessel is on the port, it requires power. We do have project looking at onshore power system, providing the electricity to the vessel. We do have project looking on how to load, unload containers from the vessel to the port. And some hydrogen valleys looking into port as an ecosystem for hydrogen technologies. That will be subject of talk and session later on. Now I'll move into the rail. Project FCH2 Rail has been putting 1.2 megawatt of PEM fuel cell on board the regional train that has accumulated more than 10,000 kilometers on the trucks in Spain and in Portugal. The last stage of the project looked into the TCO analysis. Still, you cannot compete the diesel generator if you want, but there are clear guidance on how to reduce and improve the TCO on trains. Aviation, let's go into the skies. 2 streams of research, one on the fuel cell, next generation high temperature fuel cells, but as well the high power demanding fuel cell for the aircraft. This will be Brava, which will be presented later on. And on the liquid hydrogen tanks that are conformable, meaning that they could fit with their shape within the fuselage of the aircraft. I would like to highlight Synergy with the Clean Aviation Joint Undertaking. Us, Clean Hydrogen GU, developing fuel cell technology blocks so that later in time, for the 2026 call of the Clean Aviation Joint Undertaking, the first, the maiden flight of these aircraft could be done. Conclusions. Hydrogen in transport is a reality. We do have buses, trucks, garbage trucks, working with high reliability. The new markets are scaling up, multi-megawatt fuel cell system for the maritime especially, and the long-haul trucks showing pathways for the commercialization and deployment. Technology gap remain, but they are narrowing. Durability, I've indicated that earlier. The high-power fuel cells, the storage, especially liquid hydrogen, and the manufacturing scale-up. So still work to be done. And one last item, it's regarding the investment, the policy alignments that are essential to determine the speed at which the market will adopt hydrogen solution. Ladies and gentlemen, this was in a nutshell the portfolio of projects on hydrogen for mobility. I have now the pleasure to call on stage our first project coordinator, who will highlight the ambition and the objective of her project, Isabelle Cole, for the project H2O. Isabelle, the floor is yours.
Great, thanks everyone. Yeah, I'm really excited to be here today to introduce you to the H2 Hall project and join the panel discussing hydrogen mobility and the various projects that are working on that in general. My name is Isabel Kuhl. I'm a senior consultant and project manager at ERM, which is a global sustainability business. So I sit in our low carbon solutions team, and we work across a number of different sectors and technologies, including but not limited to hydrogen. I have 5 years experience on EU flagship projects, and for the last year I've been the main coordinator of the H2 Hall project. At its core, H2 Hall is working to develop, deploy and operate 16 fuel cell trucks across 4 different countries in Europe, as well as developing and operating the associated hydrogen refueling infrastructure that will support these vehicles and help to build up ecosystems across Europe. By the end of the project, H2 Hall will have clocked up over 2 million kilometers of day-to-day driving, helping to prove the viability of hydrogen technology as a viable alternative to diesel for heavy-duty, long-range fleets, and hopefully ultimately developing the business case for further rollout of the technology across Europe. So I mentioned ERM, but you can see on the bottom of the slide here the other partners that we have in the project. So we have 2 different vehicle manufacturers, Iveco and VDL, as well as a number of other component and infrastructure suppliers. We also have a number of cross-cutting partners supporting in the dissemination and analysis of the project, not to mention our wider observer group made up of various customers and other stakeholders in the sector that we meet with periodically. H2 Hall began back in 2019, so it's been going on for a little while now, and it's now set to finish at the end of 2026. So we're about to go into our final year on the project. As you can imagine, that's a lot of progress to fit into 10 minutes, so I will try and summarize some of the highlights. But the first few years of the project were really focused on the kind of the development, design, specification of the trucks and of the refueling stations as well. Before moving into the build, and then about a year ago we moved into the deployment and operation phase. So in Q4 of 2024 is when we started putting vehicles on the road and deploying them, and we've now clocked up over 140,000 kilometers driven at the moment, with the operation in customer hands of 13 trucks and 5 hydrogen refueling stations within the project. So as we move into the final year, our focus is really on this kind of monitoring analysis and ultimately the exploitation of results. Obviously, we want to clock up as many miles as we can, get as much operational data, and then being able to use this to feed back to policymakers and share the wider learnings of the project. So moving into the specifics a little bit, I mentioned we have 2 vehicle manufacturers. The first of these that we can look at is Iveco. So Iveco are planning to have 12 vehicles within the H2 Hall project, 9 of which are currently in customer operation. So these are in Switzerland and Germany with the customers that you can see on the screen. So we have 4 vehicles in Switzerland being operated by Migros and Leclerc, and then 5 in Germany with BMW, DHL, and Hylane. As I mentioned before, these vehicles were ready for operation at the end of 2024. This is a little bit later than was intended in the project. There were some delays during the construction phase, and this meant that by the time the vehicles were ready, there were some potential issues with customers being ready to then deploy them and move on. So the approach that was taken by Iveco was a kind of soft start at the end of 2024, the beginning of operation of the trucks in a sort of phased way before moving into full customer deployment throughout 2025. There have been some teething issues. In particular, there's been some significant downtime of some of the vehicles, usually not due to problems with the fuel cells, usually other issues, which is reminiscent of what was said earlier about the electrolyzers. But we're starting to see the reliability increase and the performance increase, which is allowing the customers' confidence in turn to then improve. And we now have over 100,000 kilometers driven by the Iveco fleet. The other OEM in the project is VDL. So VDL have 2 core trucks within H2 Hall, both of which are in customer operation with Colruyt. So you can actually see the routes that these vehicles are currently driving behind me. So these are mostly based in Western Belgium, as you can see, operating between Colruyt's distribution centres and their supermarket stores. So similarly to with Iveco, Colruyt initially started with a bit of a phased approach in order to build confidence and reliability with the trucks. They operated with a lighter payload, less intense operating schedule. But what we've seen in the last few months is actually really excellent performance from these trucks and really high driver satisfaction. And Colruyt have now been able to move on to a phase 2 approach of their operating schedule, which can be seen on the slide here. So these trucks are now in operation for 2 10-hour shifts a day, with 4-hour slots in between that for refueling and a change of driver. They have an increased payload, and this is actually the exact same operating schedule as as Colruyt uses for their diesel trucks. So these 2 trucks are now fully integrated within Colruyt's fleet. They operate on the same schedule to the same payload as the diesel trucks and are performing well. So we're getting lots of positive feedback from that. If we look at the station side of things, so I mentioned we have 5 stations within the project. This is across 4 sites, and 3 of them are funded. So try and remember which ones. So we can see that in Switzerland, we have the Rothenburg station, which is operated by H2 Energy. In France, we have the Fos-sur-Mer station. This was originally built and developed by Air Liquide, but recently has been transferred, so is now in the operation of Thiel Mobility. In Belgium, we have the Oligny station, which is operated by DATS 24, which is part of the Colruyt group. And then finally, in Germany, we have 2 stations, one in Nuremberg and one in Leipzig, operated by Total Energies. So these 2 in Germany are the ones that are not directly funded by H2 Total Energies is a non-funded partner in the project. But having said that, both of these stations are being used on a daily basis by the H2 trucks. So that's their kind of main customer base at the moment. So the Iveco trucks in Germany are refueling daily at Leipzig and Nuremberg, slightly less, not daily. And in Belgium, we have the VDL trucks refueling daily at the Oligny station. So this is their main base. They are able to do their shifts and then return back to Oligny to refuel every day. In Rothenburg and Fos-sur-Mer, these stations are also both operational, open to the public, but they are not being used currently by the H2 Hall fleet. They get their main customer base from other trucks outside the project. So all are in operation. As you can see, there's a bit of a range of when they came into being open, with Rothenburg being the first station opened in the project back in 2021. So they've now been providing nearly 5 years of data, which is great to see. And then we have more recently, the German stations were opened this year, and Fos-sur-Mer, although opened for testing in 2023, is actually now open to the public as of last week, I believe, maybe the week before. So we're starting to collect data. Obviously, we have a lot more from some than others, so the results are not the easiest to compare at the moment. But what we can see is that all of them have an average availability of over 90% at the moment, some of them significantly higher than that as well. So I think to kind of wrap up, as I mentioned, we're kind of going now into the final year of the project. It's been great to see, I think, over the last year how the operation is developing, and we're starting to get data and results coming out of that. So our focus now is really to continue the operation of these trucks, continue to scale it up even more, I think particularly in some of the regions. I don't think I did that. Particularly in some of the regions, we are still having issues with the kind of reliability and repairs that are leading us to need to look into that. But our focus now is, on the analysis then of the data that we have. So at the end of the project, we'll have extensive reports coming out, life cycle cost, well-to-wheel, other analysis being done of the data, which will then hopefully feed back into sectoral and policy recommendations. I will take the hint from the slides and leave it there. But thank you very much. I think it's a really exciting time for H2 Hall and hopefully for hydrogen mobility in general. So if you have any questions, I will take them in the panel or afterward. Thank you very much.
Thank you very much, Isabelle. Nudging, think about a question, time to note them. We'll be talking about hydrogen, we'll be talking about port. Logically, I invite Project H2 Port to introduce their ambition and achievement. So I'm calling on stage Mr. Aurelio Lazzaro from the Fundación Port de Valencia. Aurelio, and I hope you won't have to play with the slides.
Thank you very much, Lionel. It's a pleasure for me to be here today and talking about H2 Ports project. H2 Ports project has been the first operational experience using hydrogen in ports and also probably the most ambitious one. It's also a bit emotional because this presentation means that we are arriving to the end. The project will conclude just next month. And I'm going to try to explain more than 6 years of project in 10 minutes, but let's see. Let's start by where. This is the port of Valencia. This is where these hydrogen concepts have been tested. The port of Valencia is not a lab, it's not a test center, it's an actual port and a very busy one. We move over 5 million containers every year, more than 750,000 passengers. We have 3 different terminals for container. We have 3 terminals for passengers, a couple of terminals for liquid bulk, a couple of terminals for solid bulk. So it's a huge challenge to try these innovative concepts in a place where the standards of safety and operationals are very high. The port has the objective to become net zero emission by 2030, and we are evaluating the different technologies that may help us to achieve this very challenging goal. And hydrogen, of course, is one of them. This is the core concept of the project. We have tested 2 hydrogen power machines in 2 terminals of the Port of Valencia. One is a rich stacker that has been tested in the MCC terminal. A rich stacker is a machine that makes small movements with the containers once they are in the terminal, like piling them or loading it into the trucks or trains. And we have also tested a yard tractor, that is a tractor head that has been tested in the Roro terminal of the Grimaldi group. The project started back in 2019, where at that time hydrogen technologies and imports were just aspirational concept, and has lasted until next month. We'll finish. So it has been a very long project, facing many difficulties like COVID, supply crisis, many different things. And well, we are now reaching the end of the project and the testing period. The project has been coordinated by us, Fundación Valencia Port. We are an innovation center related with the Port Authority of Valencia, that is also part of the project and has supported the project from the very beginning. We have 2 research institutions on board, the Centro Nacional del Hidrógeno, the Spanish National Hydrogen Center, Athena Group. We have different partners coming from the industry, like Carburos Metálicos, that is our hydrogen supplier. We have Heister Jail, that is the manufacturer of the rich stacker. It's let's say, the reference manufacturer of hydrogen of port machinery worldwide. We have Ballard, that is the manufacturer of one of the fuel cells that was used in the yard tractor. And we have Enagas, that is the Spanish national TSO, due to their experience in providing gases to industrial complexes. And at the end, I mentioned the terminals, the end users, because at the end, they are the ones that are trying the technology, and they are the ones that are interested in seeing how they perform. And potentially, they're the ones that are going to keep it. So they are actually the most important part of the puzzle. The project started back in 2019. During the first years of the project, these prototypes were developed. From November 2022, that was when the HRS started the operation, until December 2023, that we received the last of the 2 machines. This was the period devoted to the development of the prototypes, and since then, and during 2 years, these machines have been tested in the 2 terminals of the port. This is the hydrogen refueling system that has been designed by the Centro Nacional del Hidrógeno. Both machines, they cannot abandon the terminals due to port laws, so we needed to provide the hydrogen to the terminals, and that's why we went into this mobile concept. Our hydrogen provider, Carburos Metálicos, discharges the hydrogen at a low pressure tank, and well, it is compressed, and it goes into the terminals in this mobile unit that carries the compressed hydrogen and performs the daily refuelings. The mobile unit has a total capacity of 55 kilos, more or less, of hydrogen at 350 bars, able to deliver at that pressure, and a flow rate of 3.6 kilos per minute. Taking into account that the reach stacker has a tank of around 30 kilos, and the yard tractor of around 12, this means that within minutes we are able to refuel the machines in the same way that the diesel equivalents do. This is the reach stacker already operating in the port of Valencia. It's a complete new design from Heister Yale. It is powered with 2 fuel cells of 45 kilowatt each, developed by Nuvera. They work as a reach extender. They keep at nominal power, loading the batteries that at the end are the ones managing the entire energy system of the reach stacker. And the main objective is to perform at least, or in a better way, than the current diesel equivalents. And for that, we have the objective of, well, reducing or demonstrating that we are able to reduce, in the long run, the total TCO, the total cost of ownership. We know that these machines are going to be more expensive than the current diesel equivalents, but with a lower maintenance cost and with a lower hydrogen cost, we can take advantage of the improved energy efficiency that these machines are able to have, performing in the kind of movements that the machine do, in compared with the diesel equivalents. And this is the yard tractor that is being tested at Grimaldi terminal. Instead of a new design, it's a retrofit from a diesel equivalent from Terberg. It's also a very important manufacturer of port machinery. Athena replaced the diesel thermal engine with an hydrogen powertrain that is composed by a fuel cell, the different tanks, and the battery system of 25 kilowatt hour. And this machine does what is now showing this video. They move the platform of the trucks into the vessel. This requires that in a very specific part of the cycle, it requires a lot of power. So this machine is working as an hybrid system. It is able to deliver power from both the fuel cell and the battery system. And the entire energy management system has been designed by Athena. It was a very good job. After more than 2 years of operation, we have been gathering data related with the operation of these machines. This is not complete. We are going to keep the testing until the very end, until the end of December. But during these years, we have tested the machines for more than 1,000 hours. We have used more than 1,000 kilos of hydrogen in real operations, and more than 100 cycles, meaning shifts of operation during these years. And the same for the HRS. It has been tested extensively during these 2 years, and we have this data that somehow is the legacy that the board is going to left to the future projects involving hydrogen technologies import. I think that this technology has been tested where it should be tested, that is in the field, compared with the machines that are currently running the port. And it's a very valuable operational experience for the future of hydrogen projects in port. And I would like to thank the Clean Hydrogen Partnership, and especially Lionel for his support during these many years, not always easy. And if you have any questions, I can address them during the debate. Thank you.
Thank you very much, Aurelio. I hope this could be replicated to other ports. Maybe it will be a question for the Q&A. Now, our next speaker will mention hydrogen in maritime environment, project H2 Marine. The coordinator is Mr. Kyriakos Panopoulos. Kyriakos, the floor is yours.
Thank you, Daniel. Hello, everybody. So all this hydrogen has to be used in ships. Not that ships are not, let's say, the biggest CO2 emitter, but certainly it's a backbone of the energy transportation and the fuels transportation. And also their industry is facing huge pressures to decarbonize. So hence the interest. We are almost, let's say, just past the middle of the project. Our project ends in the middle of 2027. We are 13 partners from 5 European countries, 4 EU, and 1 which is Switzerland. And we want to build 2 actually stacks from partners from the consortium, 2 stacks of 250 kilowatts that will be able to upscale later on in megawatt, in tens of megawatt systems. Of course, one of the things is to test them, not to put them on the ship, but to test them in relevant environments. If you see a glimpse of the consortium, there is partners from VTT, PowerCell, which is building one of the stacks. EH Group is the other one from Switzerland. Then there is TKMS, ThyssenKrupp Marine Systems, who is acting as a shipyard with a lot of experience from hydrogen introduction into vessels. And then manufacturing, Dana, ZSW is doing a lot of our testing. University of Fraunhofer is developing diagnostics, Greenerity with the manufacturing, and of course EPFL, who is also present in this room, and Beyond Gravity, who is doing tests with vibrations and tilting. Then in Greece, we're coordinating at CERT. We also have a club for dissemination, and notably Kleos, last but not least partner, is representing 3 of the major ship-owning industries that actually drive this process. Maybe I will skip this and go directly to our philosophy in the project, which is, let's say, the work packages was the previous slide. What we want to have is to design a fuel cell that is fit for the end users' purposes. So we want to define maritime environments. We want to define the ramps and the requirements of large ships. Then we also want to develop ways of testing diagnostics. We also want to put the focus on critical components. Then, of course, all of this is building short stacks, but also at the second half of the project, where we are now manufacturing 250 kilowatt stacks that will be tested for several hours, also with accelerated stress testing. in order to prove the validity in relevant environments to the maritime sector. Then a very important exercise, because as you realized, we have two manufacturers that sort of competing each other, but a very, very interesting thing that both work on, and the rest of the partners around them are assisting, is the design and the upscaling towards a 1 megawatt super stack, which can be also fit for 10 of megawatt scale system. That exercise, together with the validation of the 250 kilowatt stacks, is, let's say, the cornerstone of the achievement we're trying to have in H2 Marine project. Eventually, we will have a costing exercise where we can see how much this application of this technology would cost to the maritime sector in order to adopt it. Now, as I said, we are building two stacks, 250 kilowatt stacks. There's a lot of horizontal work which can also be helpful to other fuel cell manufacturers about diagnostics and testing. So we're trying to devise ways of monitoring health of critical components online. That is very, very important also for the maritime industry. Then we want to achieve a lifetime of the stacks of 40,000 to 80,000 hours of operation. And of course, the cost implications if one wants to compete with internal combustion engines, which are robust and they have reached, let's say, a level of maturity that allows them of low capex. Costs have to go down to €1,000 per kilowatt by the next 5 years or so. All of this will have to be put also into the design of a larger super stack towards 10 megawatts of scale of systems. That is also probably the subject of the follow-up project to validate, and then eventually to put it on a ship. So if I talk about a little bit about the results we have so far and the ongoing works, one of the things that one can see here is that we have defined accelerated stress tests in order to prove what are the best components to use. We have defined also tests for particulate and checking the quality of air. An important thing that we have done was also to develop a carbon-13 method that can monitor online the carbon corrosion. That is also very, very important. Furthermore, diagnostics for monitoring hydrogen and water levels. What we imagined as a use of this system was the application in liquid hydrogen carriers, but of course the call itself was agnostic to the fuel, and these tests are also good for other means of supply of hydrogen. So we focus on this in terms of what we want to achieve in RAMs and operational parameters that these fuel cells would have to prove. Then one more thing that I have to say is that small developments have been done, improving the MEAs, improving the gas diffusion layers. There was also developments that are now frozen about the balance of the stack. That was very important, and also manifold designs that would allow replication and upscaling. So this was also performed. Now we are in the phase of constructing the two stacks. The relevant partners, PowerCell and EH Group, are constructing the stacks. And of course, the ongoing work on upscaling the units to a super stack of 1 megawatt that could be replicated and reach 10 megawatt systems for power supply for propulsion of ships. A lot of issues in this horizontal work package also concerns everybody in the stack business, which is about how to integrate peripheral systems, supporting systems such as cooling system, manifolds, operability, access to the systems, and also how to maintain operation of the stacks, even if one stack is let's say out of operation. So all of this is very important for the maritime sector. A ship cannot lose its power in the mid of the ship, and the internal combustion engines that this technology is competing against is already one of the most robust technologies that the industrial revolution has come up with, and eventually right now we are competing with them. So the impact is very important. We want this hydrogen to be able to use it in ships, and hence the fuel cell is the most efficient way of doing it. The PEM fuel cell, we want to minimize battery operation, reduce greenhouse gas emissions, and of course all of this has to happen in Europe. So supporting European manufacturers for this, creating jobs for the energy system of the future for maritime applications. So with this, I would like to thank you. There's the website and also there our contact details that you can ask questions, of course, also later on. Thank you.
Thank you very much, Kyriakos. You heard scaling towards megawatts. We have heard from H2All, H2 Port, H2 Marine. You wish it would have been a Connect 4 or 4 in a row. The next speaker will address hydrogen and planes. Okay, so I have the pleasure to invite on stage Mr. Jörg Dappermann from the project Brava. Thank you.
Thank you very much. And talking a bit about why we do what we do, I want to have a short review of the Airbus ZEROe project. There are many similarities with the speeches we just heard. One example is this is the one aircraft, 10 megawatt power propulsion, 100 passenger, 1,000 nautical mile aircraft we're targeting at. It has liquid hydrogen in the rear of the fuselage. It has 4 engines. We have all the requirements of many speakers we heard before: liquid hydrogen storage, long durability. But one of the elements which we might be different from all the others is our requirement in weight, because we want to fly, and weight is the most important element. So we talk 10 megawatt fuel cell drivetrain at the lowest power, or at the highest gravimetric power density possible. This is the engine. I'm talking about the colored elements. We call it the power generation system. It consists of stacks. This is one engine, 10 megawatt per aircraft, 2.5 megawatt per single engine. We're talking about 300 kilowatt stacks, 8 each, so that's 2.5 megawatt. We investigated in Brava breakthrough technology bricks, deviating from, let's say, a baseline approach. Baseline would be liquid cooled. Brava talks about a different solution. Baseline is classical ionomer and PEM technology. We're looking into differentiation. As we are investigating a maximization of power density of the entire power generation system, we're trading individual equipment. So not the lightest weight stack is the best stack, but it's the one with the best combination of a cooling system and an air supply system. So PGS weight optimization. One quick word about Zero E. Airbus announced a slight modification by the beginning of the year. Sometimes it was misinterpreted, but the message is Airbus continues in Zero E in fuel cell, hydrogen, electric aviation, and we're investing 3-digit millions a year in this project. Next. Oh. The Brava project is structured similar to many others, work package management, dissemination, but I'm talking mainly about these four. The thermal management system, there were two elements with all European partners. One is two-phase cooling, and the second is 3D manufactured heat exchangers in order to have the lowest weight and the highest volumetric density. Then we're talking about fuel cell stack technology bricks that we wanted to and will replace in the fuel cell stack. Then an update on an air supply system, an aviation-grade air supply system. And then in work package 6, the integration of all these elements plus other elements in order to optimize the power generation gravimetric density. So the first work package, thermal management, two-phase cooling, was elaborated in close collaboration with NLR in the Netherlands and our stack supplier, Aerostack, in the south of Germany. And the approach was that we wanted to replace a classical liquid EGW-based cooling system, or actually a weight transport or a heat transport system from the stack to the heat exchanger. And the intention was to use evaporation of a media and to use the latent heat in order to have a less weight transport of the heat. And it was the first time that a 20 kilowatt two-phase mechanically pumped loop cooled system has been built, has been commissioned, and has been successfully tested. The rotation indicates that the test rig was fully movable. It intended to emulate all the maneuvers of an aircraft, but also to demonstrate and prove that the orientation of the media has no impact on the operation of the system. The only necessity is that when the system starts and the two-phase is yet liquid, the pump needs to be at the bottom. Once this has been shown successfully, the NLR built up a 200 kilowatt two-phase cooling system based on the learnings of this. And in parallel, our stack partner Aerostack also tested their stack technology and their flow fields and bipolar plates using two-phase cooling, and the result was that we identified control schemes in order to make it work to operate at two-phase cooling. The benefits of this two-phase cooling innovation is a lower fluid and heat equipment mass, so we more or less cut the weight of the media into half, minus 58%. We had a much lower liquid or a much lower coolant pump parasitic load because you need to transport less media. So we have an 88% power reduction, and the liquid cooling loop is a high parasitic load of a fuel cell system, thus impacting the overall efficiency of the fuel cell system. And it is the world's first aeronautic fuel cell stack, which is the Aerostack 3.1, which is the first fuel cell stack that was intended to fly on our A380 flight test demonstrator, operated with a two-phase cooling approach. The second element of the work package 3 thermal management system is the optimization of volume and the reduction of weight of heat exchangers. So it's a heat exchanger, on the one hand addressing the two-phase cooling, but in this case targeting a classical liquid cooling loop. So it's a liquid air heat exchanger. It's 3D printed for volume and mass optimization. It has all the heat exchanger walls, the manifolds, all printed with a mid-scale with an aluminum, and the analytical improvement of a full-size heat exchanger would have been 20% lower mass, 50% lower drag due to optimization of the air channels, because cooling air is a major contributor of drag in an aircraft, in a fuel cell air-cooled aircraft, and the drag reduction of the heat exchanger is a key element. So we reduced 15% of the drag and had about 30% smaller volume. The 30% was the target. We achieved only 13%. So that is one of the outcomes of this project. We manufactured, or actually the project partners Morpheus Design and Madrid in Spain, they manufactured thin wall specimens of 0.5 millimeter thin aluminum walls in 3D printing. It has been designed, it has been built, and then it has been fatigue tested. So vibration in an aircraft is a key contributor to fatigue and stress. And these heat exchangers have been vibrated towards aviation requirements, especially for propeller aircraft. And also shock tests have been performed. They have been successfully achieved. So the benefits is a potential decrease in mass and drag of the heat exchanger. The heat exchanger volume might be reduced by studying even further by studying the heat exchanger integration into an aircraft and optimizing this and making it possible due to 3D printing manufacturing. The work package 4 is dedicated to the fuel cell stack and especially the membrane electrode assembly development. The target was to develop a membrane with a durability and operation of larger 20,000 hours. I read 60 to 80,000 hours of stack operation in the maritime application. That's an impressive number. We think that the optimum between lifetime and degradation, higher power consumption, lower efficiency, higher heat exchange is for aviation in the range of 20 to 25,000 hours. So the target was to have a 20,000 hours durability of the membrane. Of course, these 20,000 hours have not been tested in the Brava project. We were able to test a lower duration. I think 800 hours of membrane testing have been achieved within the project, and the 20,000 hours have been extrapolated and the target can be achieved. Membrane conductivity, so the proton conductivity is a target which improves efficiency and improves performance, so reduces stack weight. Target was to be beyond 20 millisiemens per square centimeter, which might not be an impressive target, but we're looking at a high operating temperatures of 105 degrees and a very dry air operation with a relative humidity below 20%. And the main reason is high in the air, it's bone dry, so we don't have any humidity. And we intend to reduce equipment as much as possible, so flying without a humidifier is the target, thus the low relative humidity target. The MEA performance target was defined in Brava to be 1.75 amps per square centimeter of power, or of current density of the active cell, but at a efficiency of 60% equals 0.74 volt. The result, as of to date, have been 0.8 amps per square centimeter at these tough conditions, with an improvement of up to 1.3 amps per square centimeter being feasible within the Brava project timeline until mid next year. The MEA size that you see here that has been produced by these partners, Aerostec again for the stack, Heraeus, Technische Universität Berlin, CNRS in France, Sciences-Q. They achieved a MEA with 35 by 20 centimeter size, so the MEA size is sufficient in order to cut enough MEAs to allow for a high power stack buildup. So it's not a small scale MEA production, but a bit of a bigger one. So one full stack could be manufactured. And the benefits of this approach is the partners used a Tolon reinforcement membrane, and that would be the first PTFE-free membrane. Time's over. Air supply, large integration of an air supply system, good achievements with the partner Liebherr, lightweight, full power for aviation applications to produce air for fuel cell operation in high altitude. And finally, the work package 6, the integration of all the Brava elements into an engine plus additional equipment, and especially additional equipment reduction. So we achieved a power generation weight reduction of 30%. We achieved the durability requirements, and we have a significant improvement in operation and maintenance cost. Thank you very much.
Thank you very much, Jörg. I invite our 4 speakers to sit on a beautiful sofas here. I promise it we'll do it. Q&A from the audience. Take advantage of your presence today and the one of the speakers. But we'll put a frame. So it's just one question per individual. Please, no follow-up, no comments. And the speakers will have a joker card. So if they don't want to answer, joker. Everybody has a right to a joker. And as a moderator, I will try to correct the imbalance in transport mode if there are any. So, audience, now is your moment. Any question to the ladies and gentlemen? Yes, please. Gentleman here.
Hello, Brad Leidberg, University of Luxembourg. For the colleague from Airbus, if you achieve all of the goals that you set out, and for some of them you have and others not quite, and with the expected load of hydrogen that you expect on the aircraft, what range will it fly?
The target, the target, and we think it's achievable, is 1,000 nautical miles. That's roughly 1.2 tons of liquid hydrogen per mission.
Thank you.
There was another hand raised. Yes, gentleman.
Good afternoon. My name is Klaus Stolzenburg. My company was a partner in the JIVE and JIVE 2 project, so on bus demonstration, fuel cell bus demonstration. And a key observation in the projects was that the refueling stations, in terms of their performance, were not satisfying. So regarding availability, reliability. And the bus operators have very strict expectations as to the performance of hydrogen infrastructure, because next morning at 6 a.m. or so, the bus has to be at the bus stop on time. So if I cannot refuel, it's a disaster. The figures I saw for H2Haul and for the H2 Ports projects regarding infrastructure or refueling station availability, performance, number of fuels that could not be performed were not, as far as I saw them, not really exciting. So I wonder what the view of the vehicle operators in the projects is regarding the refueling infrastructure.
Isabel, joker or not joker?
Is that?
Yeah, it's work.
Okay. Yeah, I think it's a good question. I think refueling downtime is definitely a problem that we're having, especially with kind of an early technology where you don't have this whole network yet. If one station is down, then that can kind of put a pause on the whole fleet. We had an incident over the summer where that happened, and the trucks were just completely grounded for 2 weeks, and it prevents you from kind of doing anything, which is unfortunate. I think what we're seeing is the availability is going up for some of the stations. They've only been in operation this year. I think for Rothenburg, that's been in operation since 2021, it's been very consistent and also increasing over the years. So customers are happier with that, but I do agree. I think it's the same as with Drive and Drive 2. We're having the same issue in H2 Hall. And yeah, we would like to see it increasing. Hopefully it will over the next year.
In H2 Port's case, the HRS was a specific design to supply hydrogen for the project. So in this scope, the results are satisfactory, but we know that in case there is a wide replication of the project and each terminal has 5-10 machines powered with hydrogen, the solution is not valid anymore. Then they will need to have an HRS within the terminal. This is something that's a bit scary for the terminal operator, to have one system like this within the terminal. So this is going to be one of the main challenges in order to achieve replication of the project and to have a fleet of hydrogen-powered machines within the terminals, to have a consistent and reliable way of supplying this hydrogen, and that the terminal operator feels comfortable with it within the terminal.
Thank you very much. Other question from the audience? Yes, the gentleman here.
Hello, Sylvain Bush, Johnson Matthey. Question mainly for Jorg about the operating condition for the stack. Because I was always under the impression that any PFSA base, which is, you said there was a PEM base, CCM that was used in your stack, was always going to be operating at the lower end of your requirements. And that your true need was higher temperatures. So what materials do you actually need from us to be able to operate at those conditions?
Well, I stated the dry and high temperature operation at 105. We're, as a research, investigating higher temperatures, so HTPEM as well. But so far, the LTPEM is the most mature and the most reliable technology brick. So for the time being, we'll continue with with LTPEM. And there's nothing more I can say. I'm not sure if I understand the question well.
I just want to see you now using his joker, so that's all.
You see, it's very transparent in this panel. A question from the gentleman there.
Michael Kuznetsov, Fraunhofer IKT, Germany. I have a question to all of you, and it is about purity of hydrogen you have in your systems. What grade of hydrogen you intend to use?
Maybe I'll start. I use liquid hydrogen, so it's pure almost by design. Particle impurities, metal particles, are one of my personal concerns, or our concerns. And that's not coming from outside, but partly also from within the system. So we need to be able to cope with this. But VOCs would not be that big of a problem in liquid.
Yes, Kyriakos, if you want to comment.
Yeah, also in our project, clean hydrogen, pure hydrogen was used. The project is agnostic to the supply system, so that is not in the scope. Hence, we wanted to see the integrity of the fuel cell stacks in maritime applications. Of course, in studies, we also consider reformates or derivatives of reformates.
In the case of H2 Post project, was fuel cell quality, and it is guaranteed by our hydrogen supplier, Carburos Metálicos, so in this sense.
Thank you. There was a question. This part of the room. Maybe a maritime question.
Thank you. Mathias Gerard from CA. My question is about what do you think about the position in the future of the solid oxide technology, specifically for multi-fuel application, not only hydrogen, for your different heavy-duty applications that you have shown?
I would say because the question does not relate so much with the talk or the project from the speakers, we will not take the question. Apologies for that. But I would rebound a bit on the scale-ups, the multi-megawatts for Maritime. So Kyriakos, what are needed from H2 Marine to go into the megawatt scale?
So it's a lot of development. First of all, everything has to fit in a way that allows robustness to prevail. So the systems have to be designed in a way that the upscaling together with the integration of peripheral systems, cooling systems, air supply, filtration of air, all these, you can have individual systems serving each individual stack, or you can have, let's say, larger systems serving several stacks. So all of this design is still a study, and the upscaling needs to be done in the megawatt scale. And then from that on, and once this is proven, we can go even to tens of megawatts designs. So now we are in the step of testing the robustness of the key element, let's say, in this exercise, and try to imagine how this would fit in the upscaling. But there's a lot, and you heard also before that all the peripheral systems are the ones that do the damage. So the way you integrate your heart around a working body of peripherals is very crucial in this business.
Thank you very much. The time which was allocated to us is now unfortunately elapsed. So we've been speaking about trucks, aviation, maritime, and non-road machinery. This was an essence of what the program does into hydrogen for mobility. There are plenty of other subjects. Sorry, gentlemen. You please use the time of the network to ask whatever question you want to the panelists. Ladies and gentlemen, please join me in doing another round of applause to our speakers.
Thank you very much from my side also to the speakers, and to you, Lionel, for the moderation of this panel. Let me try to address your question, and I will say that, of course, we also look at solid oxide fuel cells for mobility applications, in particular on the maritime side. And I think the next expert talk will somehow answer to your question, probably. And I would like to now invite on stage Stefan Müller-Holst from SINTEF, from our Hydrogen Europe research, and but also our technical committee leader on hydrogen for mobility, and together with Jaap Gebrath, Secretary General Waterborne Technology Platform, and to underline how we work together with other partnerships, in particular when we talk about end users. Because we provide, do you have something to share with me? I'm listening. Okay, because I think you've seen, in particular for the end users, we are producing solutions for the different applications, and this is where most of the synergies within the program of the European Commission happen. So let's take one, the maritime one, and let's dig further. Stefan, yep, my pleasure.
Thank you so much for the kind introduction, Mirella. I'll take this opportunity to invite Jaap Gebrath from the Zero Emission Waterborne, or Secretary General for Waterborne Technology Platform. Isn't that your official title? It's great to have you here. And we have been asked to say something about the synergies between programs. And as you know, the Commission has really underlined the importance of that, not least to reach or have more impact of the total framework program over these years. You've been devoting most of your time so far since you graduated from the Rotterdam University to logistics and transport. You've been 7 years as the Secretary General. Is that so?
That's correct.
So I didn't forget anything when it comes to your background.
So far, intelligence worked. Let's see if my intelligence worked, because for this we have LinkedIn and internet, but I'm not sure if everything I digged up is true. So what I saw is that you have been chairing the Transport Technical Committee of the Clean Hydrogen Joint Undertaking since the establishment in 2008, or the predecessor, but also building a portfolio of around 45 EU co-funded projects in the framework of the partnership. And here it becomes complicated for me. You seem to have a PhD on fuel cells, so any technical questions? They are not for me, exactly. Is that correct?
Yeah, I think so. And in that respect, I think we complement each other when it comes to our competencies. Absolutely. It's a good start. So, yeah, when it comes to technology, should I say something about that, the maturity and yeah, we've seen this today, throughout the day, that yeah, it's evident that we need to work together. We need to put together the port authorities, vessel designers, energy providers, regulators. So which synergies do you see should we exploit to really enable a large-scale maritime uptake of hydrogen as well as derivatives? I think we should already now involve or include the derivatives in our discussion.
I first have to correct myself, because if I use the word maritime, I'm excluding part of the ecosystem. So we refer to waterborne because it includes inland waterway transport and the maritime angle, just to be clear there. No one in that ecosystem can do the transition on its own. If a ship owner, and the ship is only built on order, I think that's one of the fundamental cases in our sector. Only when the order is signed, the vessel is being built. So there are no tests, there is some serious productions, but limited. If the ship owner wants to build a vessel, it needs to make a fuel choice, basically on the fuel available. But the fuel supplier will say, I first need to have my off-takers in place before I'm able to supply the fuel. So there you have the first connotation between the two. That might be a bit more easy in liner shipping, but in the maritime domain, 85% up to 90% of the goods are transported in bulk tramp, which makes it overly complicated because we don't know where we are sailing. So that's one part of the story. But it also means that we need to have the infrastructure in ports. And then we come to different ship types with different autonomy, different power requirements. So there you can draft a nice puzzle. Okay, who is involved where? Which stakeholders do we need where? And what would potentially be the roadmaps to get to zero-emission waterborne transport? But maybe we can take that one a bit later. But I would have a question for you, since you are the one...
Before we skip to the next question, last week there was an announcement. There was investment in ports, 24 ports, I think, through Thinea. With that, or does news like those make you optimistic in the development of the zero-emission and low-emission shipping?
It absolutely helps. I think there was a significant amount of projects and money on both hydrogen supply and onshore power supply. So it absolutely helps in getting that ecosystem taking off. So absolutely.
Yeah.
Now, when we look at the technical part, what would be the key R&D breakthroughs to have hydrogen as an uptake in the maritime sector and being competitive at the same moment in time with ships sailing on conventional fuels? Could you give us there a bit of a deep dive?
From the technology side, there was a question about solid oxide, lagging it somewhat behind the PEM, I would claim still. PEM is close to mature enough to be entering the market, but there are two major shortcomings. One is that the optimism related to reduction in cost when production volume of fuel cells were foreseen to increase. We haven't seen much of that. And then in the meantime, we have had a dramatic increase in energy prices and energy costs in general in Europe, making even the most mature technology, in this case PEM fuel cells, it is not TCO-wise competitive. So again, there is a lot of there is some stagnation for sure. There is a development. You see the projects being presented here in the last session. So I'm optimistic, but it's still so that we need the fuel availability, which you already mentioned, and it's also that recently we've seen that some solutions looking into more a dual fuel intermediate solution that can use existing fuels as you face in the zero or very low emission fuels. Those alternatives are much more relevant. And we've seen combustion coming back tremendously, not least because the fuel cells are still relatively high cost compared to of course, incumbent technology, and the fuel flexibility is then compatible with combustion. So that's my view on these issues. Then to the derivatives as such, we were asked to say something about the synergies related to hydrogen use in maritime, but there are several other derivatives that we are discussing. We have methanol, we have ammonia, liquid organic hydrogen carriers. Where do you see let's say the maritime industry and the whole sector is focusing? Is it pure hydrogen, or is it one of the other derivatives that kind of takes the most interest?
It depends on the definition of maritime. So what we did to make life a bit more easy, maybe is say, okay, we have 110,000 vessels in the IMO registers, 12,000 inland navigation vessels in Europe. Can we categorize them in certain ship types based on power requirements and autonomy? Because certainly also the time that vessels bunker, or the times that they bunker on a voyage, is essential in the current business model. So we said, okay, we have inland navigation, where a lot of efforts has already been done, and I think there was a baptize of a vessel last year or the year before under a project from Clean Hydrogen. Short sea shipping, where I think hydrogen certainly could play a potential. We have ferries as a separate category, hydrogen, electrification, depending on different characteristics. And then we get to cruise, which is still a European product, so only built in Europe. Hydrogen, certainly not ammonia. I'm not going to say which options could work there, but ammonia on a passenger vessel, most probably not. Intercontinental, that might be a struggling block to see, okay, what would be the fuel or fuels for intercontinental, and in the end, offshore. Second part, which will make an effect on the fuel choice, is again the liner versus the bulk tram. And if we look at the 2050 target or the 2040 target, 110,000 vessels, shipyard capacity worldwide of 2,000 vessels per year. So are we timely going to new build all the vessels, or will we have a mix between new build and retrofitting? So what can we do there? Now, I don't have one silver bullet, and I don't think we will come to one silver bullet, because if we look at the energy demand, that's huge. But I think what we can look at is which alternatives will not work for certain ship types. So you can already limit it down and see how can we then come to systematically deploying certain fuels for certain ship types. So I don't have a full answer yet, but we can narrow it at least partially down.
You're referring to an average lifetime of a vessel being, let's say, 30 years, meaning that there is a huge time dependence here in retrofitting versus new vessels.
An average inland waterway transport vessel is between 40 and 60 years old. Average container vessels at the moment, 10 years, and everything in between. So indeed, you also have the long lifetime, which you need to take into account. And if I may, because also there we are different than some other sectors, majority of the ship owners is a small and medium-sized enterprise. So owning one or two vessels. So that also makes the investment decision. We need to see how can we help the SMEs in that transition. Now, I think we have another question. But as always, I mix up my notes, so I need to find it. Yeah, that's the one. How do you think that European initiatives such as the clean hydrogen and the waterborne TP can even better align to accelerate the hydrogen offtake in the maritime sector.
We've seen through some of the examples that there is already some alignment, and as I said in my introduction, the Commission has really pushed on synergies over especially since this framework program started. We have coordination meetings between Clean Aviation Joint Undertaking as well as with you, and we have developed a kind of a work share between the Clean Hydrogen Partnership versus the more application-oriented joint undertakings, where we, as the technology specific, in this case, hydrogen technology partnership, we developed the building blocks as was presented just some minutes ago, whereas the other application-oriented partnerships will then do the majority of the integration. We also done some kind of work share between clean hydrogen only focusing on carbon-free fuels, while we leave, let's say, up to zero-emission waterborne to also follow up, let's say, methanol solutions. And it's of course so that we would like to see could be a good solution to have more combined call for proposals where we try to address the chicken and egg problem more, where we fund it. It's partly already done through the hydrogen valleys, but where production and end use is there, because we've seen in the heavy duty trucks that these are funded from different sources, and it is, although they are funded, both of them, it's difficult to do the timing. One is waiting for the others, although there is available funding, and it's probably linked to both sides, the fuel supplier as well as the road transport, truck companies. They see a too high TCO, and that's initiating that waiting game. So I think we should do more joint funding, increasing the valley type of ecosystem development main thought. Which role do you see that these public-private partnerships can play when it comes to de-risking these hydrogen maritime projects from your application-oriented expertise and long experience, for sure?
Maybe also one step back. I think that we did a lot of work in having a joint call. Something is going to be announced beginning of next year.
For sure.
But it is complicated between two completely different types of partnership. But I think we did a lot, and it will normally, I think, become public beginning of next year, something like this. What is critical in terms of the partnerships is the co-financing in high capital, high risk R&D, but also piloting. As I said, if you are a ship owner, you need to pilot a new technology on board of your ship. You have the de-risking and the high capital, but also in groundbreaking solutions. Let's not overlook a groundbreaking solution. We are often looking at TRL 7, 8 and beyond, but we might miss something fundamental for the future. I think that's the biggest added value of partnerships in terms of de-risking. As you just said, I think what we should also try to combine, and there you have the price gap, because on the one hand we have the capital expenses which might make the investment decision complicated, but the operational expenses are currently the bottleneck. So how can we link it with a fair level playing field with other fuels? That requires rules and regulations. And on an international level nowadays, that is sometimes complicated, as we have recently seen. So we have to see how that stretches out, but certainly on European routes that could already be done by rules and regulations. But absolutely high risk, high capital, R&D and piloting, and the groundbreaking solutions.
I think you're fully right there. We have also on our side, I would claim that our public-private partnership, the Clean Hydrogen, established 17 years ago. I thought it was 15, 16, but of course you're fully right, Mirella. I think it's significantly increased our competitiveness over those years. It has united also the European research community to a level where we really can contribute to the industry competitiveness. And as Luigi mentioned this morning, he said, this program is Europe's coordination engine. I like that way of seeing it, because that long-term strategic collaboration is really aligning industry as well as academia's long-term goals. And as you know, we also take a more international approach when we have now invited and have accepted associated countries outside non-European countries, Canada, New Zealand, South Korea, and Japan is probably the next to be entering the program. So I think international collaboration to solve these global challenges is really some way to go. I had one last question. It's not on our note at all, but how do you see, from your perspective, the European competitiveness in, let's say, zero or low emission shipping? Are we leading the way, or where are we globally?
It depends, of course, on which segment you look in the sector, but Europe is still a technology lead. If we look at the maritime engines worldwide, 80% is coming from European companies produced in Europe or produced under European licenses. 80% of the worldwide engines. So in that sense, Europe is still a technology lead. Is that under pressure? Absolutely. Because there are more and more, what I hear, local content requirements in the Asian yard. So that is really becoming an issue. But at this moment in time, Europe is still a technology lead. Europe could stay a technology lead in clean technologies, but that requires a good MFF. Shall we leave it at that?
Yeah.
And I think what we also should mention, and it's for both sides, partnerships are a leverage in terms of public-private investments. Looking at how can we spend every euro in the most efficient way, partnerships are really there, a good example of how to leverage.
The leverage effect is huge. I fully agree. But are there any key indicators that you would mention when it comes to how should we scale this? Let's say we are in the lead, but it's all about scaling. We won't see any significant reduction in emissions unless we scale this.
I think maritime emissions even went up, as I saw last week, so we really need to go even one step beyond. One is, of course, the availability of hydrogen or hydrogen derivatives in ports of call. Second is the order books of the yards. If we don't see in 1-2 years that you see an uptake of alternative fuels in the order books and the ships are being delivered 3-4 years after, that target becomes complicated. And I think the third one, which we already discussed, how can we close the price gap between conventional fuels and sustainable alternative fuels? And that the only way is rules and regulations. I think one elephant in the room, which we might need to start involving more in the discussion, people often look at the ship owners. But the ship owner is nothing more than the owner of the ship. The one deciding on the contract is the cargo owner. So we also, I think, need to involve more and more the cargo owners in the discussion.
With that, I would like to thank you for your insights and reflections, Jaap. I think we'll end this expert talk here and now. 0 seconds left.
Exactly.
Thank you so much.
Thank you very much for this indeed inspirational talk. And thank you very much for the work still to be done on the next MFF indeed. Now, we have, hopefully wisely, decided not to give any break so that we don't lose you from the room. And you stay with us for the fun part of the day. I hope you found the day interesting, and now it's time for celebration, at least myself, with the team. I told you at the beginning in the morning, we work a whole year to identify, to propose for voting successes in both success stories coming from the portfolio of the project, coming from the innovations, coming from the best communicator, or why not the best outreach, all the awards that we will have. I do, or yeah? Ines, my angel, will help me so that I don't click before. So, it is my pleasure now to start. And to start, I would say, with our awards, with the GEO Awards. I also promised in the morning we will be joined by Hydrogen Europe Research and the awards coming from there for younger scientists. So let me start with ours, and I will start with the success stories. I'm looking at because I don't have your screen in front of me. Yeah, it's too far, I'm too old to see that one. But like I mentioned, for several years, we looked at our portfolio of projects, and you heard there are more than 100 running right now. So when we look at them, we try to pick up every year stories from projects sometimes that maybe have finished and is the last chance to promote them and to identify them. Stories coming from, you remember at the beginning of the day, I said this feedback loop and several generation of projects building on each other. And we have identified this year 5 success stories. One is the buses. I think we heard about Jive 2, and about the success of this project. One is the buses. One is the newly, if you want, area of expertise in our GU, which is the combustion, the hydrogen combustion. You may remember in the past we look at only stationary fuel cells for heat and power, but now we open the program into these new areas because we have to consider hydrogen also for large-size heat and power generation. The other one is the really basic research on MEA, on membranes, when we talk about the fuel cell. And then we have, the startups. The startups, and we mentioned here H2 Site, but we've seen several. And by the way, I was extremely surprised to see in a lot of presentation of our projects, mentioning here and there a new startup coming and flourishing out of the project to exploit really the results. And the last one is, it's another angle of the startups, which is the most developed SMEs, such as ATM Power or Sunfire. Now, we put this to vote, to voting, and especially for success stories and for innovations, we let the public decide. And I have to say, this year, compared to previous years, a lot of votes. A lot of votes, thousands of votes. The winners have won, and let me bring my numbers. A lot of the winners have won with more than 50% of these votes. And I would like to say that for the success stories, we had more than 800 votes, or about 800 votes. And the winners are Ines. Yeah? Yes. Thank you. Yeah, I'm tired. You see.
That's why I was hesitating.
Yeah. Luckily, I have my team. And to hand, of course, the award, we are pleased to get on stage again Danica Malkovic from Hydrogen Europe. And now I will announce the winner when we have everybody ready to give the award. And the winner is, what do you know? The combustion, the 2 projects on combustion, Flex for hydrogen and Helios. Yes. I'm going to get into the picture. Next to where? But we will get the chairs.
Yeah, or maybe just step down. Come down.
Down?
Maybe
better. Yeah. And that way the flow in. Yes, that's perfect.
We are not Oscars.
One more time. That's perfect. Thank you.
If you would like to say a few words.
Well, to admit I didn't prepare a speech. I didn't expect to say a few words, but I just can say I'm really, truly honored for this recognition, which is firstly possible because of a great consortium that was behind us. So this is really the recognition of a great working together, and I would like to deeply thank then all the partners that made this possible, and of course the Clean Hydrogen Partnership for nominating us, and of course hearing so much public votes. I think it was a great a great communication effort and a great public perception of gas turbines power generation, which is really great. And I truly believe gas turbines and power generation, carbon-free power generation, is going to be a key enabler for grid stability and carbon-free electricity. Thank you, everybody.
Thank you.
Okay. Thank you for the large summary. I don't have much to add to that. Only I think you're on the same page with that. Gas turbine research worldwide is really in a race for greening this delivery of electricity to the government, to the public. So that's an important aspect that we received this award, and thank you. Thank you.
Thank you very much. Thank you. I am told I forgot to invite Danica. Danica, would you like to say something? As I said, I'm extremely tired, so you have to bear with me. Thank you. Thank you very much. Okay, we'll move now to the next word, and the next word is about innovations and innovators. And I told you how we do it. We also look at the innovation radar, and we try to identify which are the most promising innovations coming from our projects, and the innovators, not per se the projects, but mostly the innovators in the projects. And again, we put it for voting, and here we had more than 2,500 votes. So a lot of votes. I have to say, for such a very technical subject, I would say a lot of votes. And I invite you, Beatrice, to say a few words and to hand the word.
Thank you, Mirella. Okay, thank you for inviting me for this Best Innovation Award. And indeed, I think this is the one where we received really a lot of votes, even more than the success stories. I'm very pleased to be here today with you, and I see already that the winner has been announced by the slide, so there was not so much to say about the six projects, but competition was very tough. Perhaps we can go back just for a second on the projects, which were 6. So you see also for recognition of the other projects. So AMPS, it's a project on automating SOC stack manufacturing for high-precision hydrogen technologies led by Elcogen OY. Then IP3D will come back in a second. Then we have the project Single, so modular stack design for ammonia dehydrogenation and hydrogen production, led by Core Stack Membrane Science AS. The project Elvis, which concerns safety solution, innovative safety solution for cryogenic hydrogen transfer in mobile application, again led by a consortium with Norges Teknisk Naturvetenskapelige Universitet in NTNU, German Airspace-Center Air Liquide, and then continuing with Flex 4H2 again, so flexible sequential combustion system for low emission hydrogen and gas blends, led by Ansaldo Energia, And then last but not least, a project, Optics, on AI-enhanced software for advanced H2 leak detection and system monitoring. But among these 6 projects, the winner, so having more than almost 60% of the votes, so 1,452 votes, is HP3D. And the project, the innovation in this project, which has been selected for the award, concerns the use of 3D printing to create solid oxide electrolysis cells with corrugated yttrium-stabilized zirconia electrolytes. So incredible innovation. And the overall goal of the project is to deliver a new generation of solid oxide electrolyzer cell stacks. So with this introduction, I'm very pleased to introduce the pioneers of the innovation for which the project is awarded. And they are Fundació Institut de Recerca en Energia de Catalunya and H2B2 Electrolysis Technologies SL on behalf of the entire consortium. So I hope the winners are here with us. Yes? Great.
Well, thank you very much. Because I think we are extremely happy. We are extremely happy for sure. First of all, because we were nominated and shortlisted, which is, I think, something relevant because you have more than 100, you said, projects ongoing. So we are extremely happy for that. Even although we were a little bit worried at the beginning because we are a high-risk project, and you know, high risk is always difficult to fund, especially when you have a technology like hydrogen that wants to reach the market as fast as possible. So we are very happy for that, first of all. And second, because it's given by popular vote, and that's wonderful. And now, after your comment on the amount of votes we had, I think that the only problem is that now we'll have to pay a lot of beers because you said 1,400, something like that. So, but in any case, we will do it gratefully. Thank you very much.
Thank you. Thank you to all. And now it's my time to hand an award. I'm putting my other hat of head of communications this time. And I have to say also with the communication officers first, in particular with, I would say, Lara sitting there, who's our, wizard on social media. She's screening all our projects and how they perform, in particular on social media, like I said, but also throughout our other events. And then with the project officers, we also look at the projects and how well they communicate, and like I said in the morning, how well they acknowledge that they get the funds from the EU and from the GU. So these are some criteria that we take into consideration when we look at the projects. And I have to say, this time, and for this time, we chose the happy family of Cosmic projects. You may remember, and you saw the Cosmic project presenting before, there have been several projects on compressors, and very proud that this year, for their efforts in communication in particular, we have selected them for getting the best outreach. Cosmic. Yes, of course.
So first of all, thank you so much. It's really an honor to receive this award.
And I'm speaking on behalf of the entire consortium and in particular of my colleague Rami Sharouri, project coordinator. Unfortunately, he couldn't attend the event today. I would like to thank, first of all, the CHJU for the continued support and trust all over the years. Secondly, I would like, of course, to thank the entire consortium for the great results and the great collaboration. And last but not least, a special thank to one of our partners, Steinbeiß Centrum Europe. Without them, this award wouldn't have been possible. Thank you so much.
Thank you. So 2 more to go. We did already a picture. Yes, Lara, thank you. Everybody's tired, but we'll make it, I promise. 2 more. So let me move to the Valleys of the Year. Valleys of the Year, we started putting it in place a bit later than the success story and the innovation and the outreach. And also, as we saw more and more valleys becoming maybe mature from one year to the other, and we wanted to recognize their efforts in doing that, of progress from one year to the other, look at what they did in that particular year, and then maybe apply some criteria and select a few of them. We've done again the job this year. And we were lucky this year because we have the consultant with the Valley facility helping us with this analysis. So it's a very backed and justified analysis how we selected that Valley of the Year. And to hand the award, I would like to invite on stage next to me Mr. Piero Venturi. He's the Director of Mission Innovation in the European Commission.
Thanks.
Piero.
Okay. I say just one word because I realize that I'm standing between you and the upper outside. Yeah. So super quick message about Mission Innovation, that is a catalyzer of research activities on hydrogen research at global level. So the Commission is in charge, and we have colleagues from all over the world. Just to give you a flavor, you have US on board, and they are attending our meetings. That's still great. And then we have Australia, we have India, we have Chile from Latin America, and obviously we have Europeans. We have Spain and the UK that are extremely active. And we are cooperating with partners all over the world. So, for example, UNIDO, IPHE, the JU, the Hydrogen Europe Research, and other OLADE from Latin America, all key partners all over the world. We are working on research and on hydrogen valleys. For this reason, we are extremely keen to be here and to deliver this award. I go ahead?
Yes.
To the winner, that is Baltic Sea H2.
I will also keep this short. It's easy because I'm Finnish. I was involved in the planning of the Valley in 2022, and we got the idea when we were looking at the Mission Innovation Valley map, and we saw that it's empty for the Nordics and the Baltics. We couldn't have that, so we came up with this idea of a cross-border and large-scale valley, which we did, and now we are here. And that's also how we think that the hydrogen economy should be built in Europe. It should be built together and across borders. On behalf of our 40 partners in 9 countries, I'd like to thank the Clean Hydrogen Partnership for this acknowledgement of this valley that we are all so proud of. Thank you.
Indeed, a very, very ambitious valley in the Baltics and the Nordics, which I'm really looking forward to see happening. And now for the last word is the women's. It's about women's. And I got somebody over a coffee break today. I got somebody who came to me and said, I'm very pleased to see so many women in the room. And maybe it's because we do something about it, Valerie. And I would like for this occasion to invite Valerie, my director, on the stage and to introduce the award. Valerie.
Thank you, Mirella. And indeed, this award is very dear to our heart because at the Clean Hydrogen Partnership, we have nearly a perfect gender balance. And at our governance level, it's 100% feminine. So we're very proud of that. It doesn't mean that we're not excluding men, not at all. And you're still very present here. But I think it's very important that we take into consideration the role of women when it comes to science. And when it comes to clean technology such as hydrogen, because it's not really attractive most of the time. So when you look at how many women you have at the beginning when it comes to scientific studies, you have a lot. And then along the path, you're losing them. So just to remind you that when you look at gender disparities at the highest level of research and innovation, 9% of inventors are women, 9%. And 98% of EU research are failing to integrate a gender dimension. Remember, whenever we're looking at our project, you have a gender diversity question. And I'm not even mentioning how many women are CEO of startups. It's very, very low. So if we want to push for competitiveness, if we want to push for synergy, if we want to push for mitigating the risk, for combining different vision, we need to have a balance between men and women. We need to have gender diversity. So I'm really happy that many of you join us today, but you need to be many more next year. So without further ado, I'm very proud this year again because we implemented this award last year. We decided to have a specific award for women. And this year I'm very proud to hand over the award to someone who is very much committed and involved in the hydrogen community. I won't tell her name right now, so don't push it on the, don't spoil and don't put it on the screen. But she worked in high-temperature electrolysis for many, many years, nearly 20 years. She leads teams working on production, storage, fuel cell, electrolyzer, upscaling. Her activity spans from material and characterization to industrial stacks and system deployment. She's also very much involved in the different institution. She's part of Hydrogen Europe Research board member. She's a TC leader. She's also very much involved in different IEA task workforce. She's French. So now you start having an idea of who it is. And she's the Deputy Director for Hydrogen Technology in CEA. I'm very glad to call on stage Julie Mougin.
Thanks a lot, Valerie, for your kind words and for these awards. Thanks to the Clean Hydrogen Partnership. As you said, I am in the field for 20 years, so it makes me think that I am getting old, but it has also been an impressive journey. And if I remember, 20 years ago, we were much less numerous in terms of women in the field of hydrogen. And I'm very happy to see that today there are more and more researchers on the different fields, from the materials to the systems, also in industry, and also in some countries where women were not so numerous in the past, like in Japan and elsewhere. So I'm very happy to be part of the ecosystem that succeeded to make hydrogen deployed from the lab to the research, demonstration, and even commercial applications, and that women are so many to take part in this journey. So thanks again to the Clean Hydrogen Partnership for awarding me today. I'm very happy to continue to work together with all of you and to continue the journey. Thank you.
Thank you. I noticed the mistake on the slide. I could see you looking at each other. Too many copy-paste in the last week. Good. So moving on to the next awards. Now the Clean Hydrogen is happy to celebrate and ready for drinks, but I have to invite now on stage Luigi Crema, the president of Hydrogen Europe Research, and let's celebrate the researchers, and in particular the young one. And really, Luigi, I look forward to see what you are saying. Huh?
Thank you, Mirella. Thank you a lot for the invitation. I'm really excited for everything related the awards. Following even the ones from the Clean Hydrogen Partnership. Today we are celebrating, as usual, together even awards for the young scientists in Europe. Maybe a few words just to introduce this award. It's an award that we are recognizing since 2018, so it's several years that we are doing this jointly with the Clean Hydrogen Partnership Awards. For us, it's very important to recognize the work of young scientists because everything is starting from young people. And through this award, we are even trying to invite young researchers to engage in the sector of hydrogen and fuel cells, and then even recognizing their value in contributing to the success of the sector. They are really motivated. I know a lot of young researchers in Europe that are really doing something exceptional to advance the sector, really motivated and working very hard on a daily basis. Just other few words to explain how we are recognizing the awards. It's an award where we collect candidates this year, as every year, one by the other. We are bypassing the numbers of candidates. We had for the 2025 the record ever in terms of candidatures and candidates to the award. We are then analyzing both on quantitative and qualitative level the different curricula, the results, the achievements in terms of indicators, but even in terms of quality of the results, the participation to the program of the Clean Hydrogen Partnership, their support to the program, their achievement, so that the final decision is taken at the level of the Board of Hydrogen Europe Research, and then today we are giving the results. So before announcing the name, I will just read a few lines related the winner. So the first winner is in the category hydrogen production. Is driving innovation in solar to hydrogen production via scalable printed photocatalytic panel reactors tailored for cold climate and decentralized applications. His interdisciplinary research integrates semiconductor nanomaterials, system engineering, and techno-economic validation, leads the H2Bridge project to enable affordable and resilient green hydrogen adoption. And the winner for this first category is Philippe Temerov from University of Oulu, Finland. Yeah. Okay, the second award is for the category hydrogen storage and distribution. The winner is doing the research to advance solid-state hydrogen storage using hybrid metal hydride phase change materials, systems for fast cycling and compact design. It combines multi-physics modeling and prototype development to optimize heat management, achieving major gains in efficiency and cycle time. The project where he is contributing is involving next generation storage for modular refueling and stationary application. And the winner is Marco Maggini from the University of Tuscia. We are now at the third award. This award is related to the hydrogen usages category. The winner is improving fuel cell powertrain efficiency, durability, and emissions through integrated modeling, degradation analysis, and real-world testing. It leads hydrogen mobility innovation across land and air transport in major EU and industrial programs. Its tools support performance optimization, policy evaluation, and climate-aligned deployment of fuel cell technology. And the winner is Marco López Juárez from the Universidad Politécnica de Valencia. And now you are saying, where is the gender balance? But I promise that at the end there will be 40% of female. So going to the next category, we are awarding the hydrogen cross-cutting activities. The winner is making advances on hydrogen safety through large-scale experimentation and risk modeling for liquid hydrogen and blue hydrogen systems. It develops probabilistic and resilience-based assessment methods to reduce hazards in cryogenic storage, bunkering, and infrastructure design. Her work informs standards and accelerates safe hydrogen. And the winner is Federica Tamburini from Alma Mater Studiorum, University of Bologna. And now a bit of suspense. We are at the last award. This is the award for the best researcher of the year. The award is recognizing developments on advanced life cycle and techno-economic assessment models for hydrogen technologies, including fuel cells and solid oxide electrolyzer systems. Her work optimizes efficiency, environmental performance, and industrial scalability of hydrogen value chains. Contributions span EU-funded projects, improving system-level sustainability and techno-economic feasibility. And so the winner of the Best Researcher Award of the Year is Xingji Wei. from École Polytechnique Fédérale de Lausanne. And I'm inviting all the winners for having a collective photo. So Federica, Xinji, Marcos, all of you, yes, come on stage. I put in the middle.
Yeah, I'm afraid we have the same problem.
Yeah, you have to step down. Yeah.
That's perfect. Thank you very much. All right, let's do this. Perfect. And one last. All right. Thank you.
Good. Now that all the awards have been given, allow me to just say a few thanks. And I'm sure Valerie will join me to say thanks because tomorrow I'm sure will be too late, we may forget. And I would like to thank, I know it's in the middle of the event, but I would like to thank the team. And we always, with this occasion, we also take our picture, the annual picture of the team. And I would like to thank, I will start, and forget me if I start this way, but I will start with the project officers. And I would like to thank them, all of them. And I would like to invite them here on the stage. Antonio, I start with you. Aguilo. Sorry to put you on the spot. Pietro. Luca. Lionel. Where is Lionel? Yes. Sorry, the light was in my face. Eleni, still around? Yes. Dionysis. Anna. Anna. Yes. These are the people behind the projects that you've seen, huh? These are the people. Ah, Alberto. Forgive me, I said it from the beginning. And Renata, yes. I should count. It's easy. To improve the gender balance. Yes, to improve the gender balance. So these are the people behind the projects you've seen, huh? And allow me to ask to come on stage next to them. Pedro is the knowledge manager. He's behind all the numbers. And now I move to communication. Lara. Lelia. Oh, you're there. And last but not least, Ines. And of course, Valerie, please join us. And because I see them in the, this is the, so the way I call it the engine. But the engine will never work without the fuel. And the fuel is our colleagues from the finance and administrative unit. And I see them in the room, and again, forgive me if I forget somebody. Nora, financial officer. Magda. Anybody else that I don't see because the light is in my eyes? No? They are working to keep the show running, huh? As we are all here. Come. Very small number of people running more than 100 projects and more than $1 billion budget. So that's the efficient team of the Clean Hydrogen Joint Undertaking, and I would like to thank them again. Thank you. And now it's time for drinks 15 minutes in advance. I hope the drinks are ready. So I invite you to celebrate. Thank you. And I see you tomorrow at 10. 9:30. Told you. I would be nobody without them. Thank you.
Yeah, 12 o'clock.